Hi. Good morning. Hi. All right, if everyone can get settled here, we'll get started. So I want to thank everyone for taking their time to be here today. We're very excited to have our fifth session for the Distinguished Speaker Series. My name is Wyatt Chafee, and together with my colleague Aileen, we run the Distinguished Speaker Series program. We really appreciate all the great feedback that we've had so far. So I want to encourage folks to continue to send your feedback to ensure that we're able to bring the high caliber of speakers that we have today, continue to do so in the future. As I'm sure you're well aware, the systems development and functional community is what's responsible for bringing the Distinguished Speaker Series. So what I wanted to do was turn the mic over to Gary Kent, who's our principal responsible for managing the functional community, for him to talk a little bit more about some of the initiatives that the community is involved with that you may not be aware of. So with that, I will turn it over to Gary, and I think we're going to switch over to the slide.
Good morning. My name is Gary Kent, and I'm honored to speak with you this morning from beautiful Lexington, Massachusetts. On behalf of Leslie DeFonso, the partner sponsor of the Software Development and Architecture Functional Community, we're pleased to sponsor today's Distinguished Speaker event. But before I hand it off to Wyatt to introduce our distinguished speaker, and recognizing that we've assembled a large body of our SD professionals across the firm, I wanted to share with you some of the exciting activities we have going on within the functional community. So on this slide, you see that we're focused primarily on three goals this year. One is increasing connectedness of with you, our software development and architecture professionals. We're trying to strengthen our technical proficiency and certifications. And as important as that, we're trying to build a base of intellectual capital to support your ability to bid and deliver and win and deliver to our clients. So in order to address these objectives, the functional community has launched several key initiatives. So you might have heard about Tim Myers and Luke Leckrone developing and deploying a cadre of agile coaches across every market within the firm. You might be aware of some of the key activities that Paul Margolin has been coordinating to engage senior leaders within the geographies. There's an exciting set of activities surrounding formulating our Booz Allen Development Operations DevOps strategy. That's an important trend in industry where we build that bridge between the development community and the operational community to improve quality of delivery to the services to the end users. We're also working hard to implement defect prevention processes and code scanning for a number of the projects that we support for software development for our clients. And Bob Harbeck and Dan Drakely are doing impressive work there. We're also driving to higher maturity levels within CMMI. So we have a plan to move to CMMI level 4 and on to level 5 so that we can bid on some of the opportunities and contracts that are coming out. And Kevin Schaff and Debbie McCoy are leading that. And Bill Olson is driving some innovative new university partnerships so that we can attract strong talent from some of the universities to work on projects that are of interest to the firm in the software development arena, and then hopefully bring those folks into the firm after they graduate. So if you're interested in any of these topics, I encourage you to reach out to some of the POCs that I've listed, or go to our newly designed community page on Hello and reach out to some of the sub-community leads in the upper right. So as I hand off to Wyatt Chafee, I'd like to express my deep appreciation for his dedication to this series of distinguished speaker events, as well as Aileen Devine, who's his partner in this effort. For those of you who don't know Wyatt, he's an outstanding software developer, architect, and leader. And he just so happens to be working on one of the most exciting new platform as a service projects at GSA. So he's probably one of the most qualified folks in the firm to introduce our distinguished speaker. Over to you, Wyatt.
Thanks, Gary. I appreciate that. So, for any of us that are involved with technology for more than a year or two, I'm sure that you all recognize that technologies continue to change. For me, as soon as I learned Spring, MVC, Ruby on Rails came out. And as soon as I kind of learned and mastered Ruby on Rails, Angular and Express and Node came out. So this is just sort of part of the trend, and I really believe that technologies like Docker for containerization and architectural principles like microservices represent the next fundamental shift in how web applications are going to be developed. So I'm very happy to introduce Lucas Carlson to guide us through some of these topics. Lucas is the author of the book that many of you have in front of you, which is Programming for PaaS. It's one of the best books I've read that gives the really concise overview of what platforms as a service are all about. He's also the founder of AppFog and serves as the innovations officer for CenturyLink. So I can't think of anyone else more qualified to talk on this topic. So with that, I'm going to turn it over to Lucas to talk about designing modern web applications. Lucas?
Thank you so much for the opportunity. It's really great to be here. That's a wonderful introduction. I wrote the Programming for Platform as a Service book, and before that I wrote the Ruby programming book. But instead of telling you kind of my credentials, I'd like to tell you a little story, because I feel like the things that you have accomplished in your life, they're great to talk about, but the things that are kind of the hardest things that have happened in your life, those are where you really learn the most. And one of the hardest things that I've ever had to deal with happened a few years ago when I was running my platform as a service. So I had a platform as a service called AppFog, and it was acquired recently by CenturyLink. And at the time, we had about 100,000 developers using our platform as a service, so deploying over 100,000 applications, which was great. We were at massive scale. We were using public cloud services. And one day, it was a Saturday a few years ago, in the evening, kids were kind of winding down. I got a call from my head of engineering. Something's not right with our servers. I think we've been hacked. The next few days, I learned a lot about myself and about platform as a service and security. It was a very difficult time for us. And I'll tell you a little story about how that happened and what I learned from that. I think it'll frame the rest of this conversation. So what had happened is a few days before that Saturday, there were a couple of 16-year-olds halfway across the world in Australia. And apparently, instead of studying for their final exams, they thought it'd be funny to go in and try to vandalize a service. Now, we had been running a system where we were actually deploying applications in our platform as a service on dedicated servers. So instead of putting all of our application code on a centralized system, which obviously could be compromised and really painful, we decided that we would take the microservers in Amazon and make sure that every customer had their own server to deploy applications for more security. But one of the things we wanted to do is, in order to both keep the cost down but also keep a very robust, reliable product, we actually had a backup. So that if any of the servers that the users were actually running on died, it would fail over to a system, so their website, even if their server died, their website wouldn't go down. So we had this shared server that was only meant for backup, almost never used, but it was multi-tenant. So these two teenagers were trying to have some fun, and one of them discovered that we had a post-deploy hook. So when you deployed code into our platform as a service, you could run some scripts and get it all set up correctly. And that post-deploy hook would run on their server. So they could basically do whatever they want. And one guy got some chuckles. He installed some malicious code, but it went on his own server. So he was only screwing up his own server. So it wasn't really that bad. But he thought it was cool. He posted it on a forum, and this other kid, this other 16-year-old, ran the same code. Now, luck would have it that one kid his server had just died. So instead of running that code on his fully encapsulated server. It was actually running on the shared server. So he managed to take down our shared infrastructure and cause a lot of headaches. We had to reboot and reinstall everything. We had to recreate every server just for security and just to make sure everything was fine. But these are the kinds of things where you get to really not only learn about yourself, but learn about what real security feels like, what real hacks feel like, and figure out what can we do to do better. So going to the cloud, going to platform as a service has some risks, but they also let you reevaluate things. And that's one of the themes in today's talk is using platform as a service, thinking about modern web architectures, not just as a how do we think about things, but how do we revamp our thinking, our thought processes in architecture overall. Using it as not just an opportunity to update some code, but update the way we think about building and deploying applications. So today, we're going to talk about what's wrong with legacy web architectures. Because I feel like if we don't talk about what's wrong, there's no point. You wouldn't understand why are we going to the future. So then we'll talk about what the future is. What is modern web architecture? And we'll spend some time digging into that and what that means and where those directions are going. Because it's a very quickly changing world. But there are some trends. And if you understand some core concepts about where things are going and why they're going that way, everything else can fall into place. So I'll try to help you understand the core concepts. Then we'll go into pitfalls. Having seen over 100,000 applications deployed with platform as a service and on the cloud, I've seen everything go wrong. So I've seen lots of pitfalls. I've seen lots of developers doing things that don't scale, doing things that break, trying to move legacy code into the cloud and it just falls apart. So we'll go into some of the worst practices when moving into a modern web architecture. And then we'll talk specifically about cloud and how to get the most from cloud. We'll touch on some topics, some modern topics like orchestration, but really we're going to focus this part of the talk, this first half, on what's modern, what's today, what's current. And the next part of the conversation after we take a break in a few hours is going to be about the future. So we're going to talk about what's coming up, what is so bleeding edge, where is it all going. So right now it's about now. And later in the afternoon will be about the future. At the end, for anybody that, you don't have to take notes because at the very end I will finish with some conclusions. I'll give you the only three things you'll need to remember from today's talk. So for anybody that happens to fall asleep, I totally understand. It's a long amount of time. But I'll wake you up at the end. I'll tell you the three things you should take away from this talk, and you'll be good. So let's start. If it isn't broke, why fix it? Well, I think things are broken. I've been a programmer for 18 years. I started in 1996. I was self-taught. I learned PHP programming back then, and then I learned Ruby later. And so I've been through this. I've been very practical during that time. One of the jobs that I did was Mog, the music streaming service that was sold to Beats, that was recently sold to Apple. And so we dealt with large databases, terabytes of information, large scale, millions of users. And what we did is very typical of kind of legacy web architectures. And let's talk a little bit about what I mean by legacy web architectures. A lot of legacy web architectures start out even in one server. It's not best practices, but even today, a lot of people will put everything in one server. They'll put the database, the application code. The application will just be in one piece of code. So whether it's a Tomcat server or a Ruby on Rails application, you'll put all the logic within one code base. And when you deploy it, you might just put it on one server. That's still done. It's one of the most common practices today. And what happens is when you're trying to scale, the first thing you might think of is okay, I'm going to add an asset server, CDN, put some CSS off-site to make things a little faster. But that breaks very quickly because there's an upper limit to what a single server application can do. There's only so much that a single server or application server can hold. So these single server, single application architectures are very brittle and fail very quickly. So what do? Well, obviously you can add some application server backends. You can multiplex it. You can add load balancers and start scaling out your system. And so then you can have HA proxy and Nginx and all sorts of different ways where you can start to try to add layers to the cake. And really, when I think about legacy web architectures at this point, I really think of layer cakes. So you add more and more layers. You put your database in its own server or cluster of servers. And so now you're feeling more secure. And actually, this is very, very common. A 3-tier or an N-tier web architecture is a very common thing, but I consider it legacy at this point. And why do I consider it legacy? Well, no matter how many tiers to your cake, when you're building a layer cake, there's so many choke points. And what happens when you have choke points is that you might have all the application servers you need, but then maybe that creates too many connection requests to your database. And your database has limited scale. And I've experienced this myself. There's only so many terabytes of disk space that can fit on one database. There's only so many connection thread limits to the database itself. So sure, I can have 1,000 or a few thousand application servers, and I could load balance them, and HPA proxy will be happy. But then the database chokes. So no matter what you're doing in this legacy cake layered N-tier system, you might think, oh, I'm doing great because I'm all N-tier. This is a legacy way of thinking. And great companies have started out this way. Twitter was built this way. Facebook, the original architectures for these things all started out in an N-tier layered cake sort of way. And that famously, I'm sure you've all seen this screen many times, Twitter had a lot of problems trying to scale their layer cake. So 3-tier and N-tier systems, they scale up to a point. But they have lots of limitations. The application servers and the applications themselves are limited by RAM and CPU. The database are limited by disk size and I/O rates. And the layer cakes, as they get more and more complex, as you add more and more code into your code base and make it monolithic, whether it's applications that are kind of like Twitter, that you're just putting more and more services within your existing code base, they end up breaking. So legacy web architectures fundamentally are fragile. So that's what's wrong with legacy web applications. How do you design a modern web application? How do you design the pyramid that will last for the next centuries? And I don't know if you can design a web application right now that will last centuries, but what is it that you can do? What is it that Twitter did? What is it that Facebook did? What is it that modern web applications do? And what can we learn from that in order to architect our applications for better scale, for better performance, for better robustness? So before I go into these slides, I'll do a pop quiz with you guys. So if legacy web applications are fundamentally fragile, what is the opposite of fragile? And please, anybody can speak up. What's the opposite of fragile? Robust. Elastic. Strong. Very good. So robust, resilient, these are the words that the dictionary would say are the antonyms of fragile. But they're actually not the opposite. They're not the polar opposite. So there's a brilliant man named Nassim Taleb who came out with a book recently. And he talks about the idea of fragility, and that most people, and in fact most dictionaries, will say that the opposite of fragility is robustness. But he says that it's not. That the opposite, the polar opposite of fragility, didn't have a word before. So it didn't have a word. There wasn't a word in the English language. In fact, there weren't words in other languages either to describe the opposite. So he gave it a word. And so the word he came up with is antifragile. What is antifragile? So if fragile is something that breaks in disorder, if fragile is something that is like a layer cake where you break one of the pieces of the layer cake and the entire cake falls apart, antifragile are things that gain from disorder. Things that actually improve with disorder. Things where if you stress it, it gets better. Let me give you some example. Fragile is like a teacup. I carry a teacup, drop it on the floor, breaks. You give it stress, and it'll fall apart. Robust is like a bar of titanium. I can drop it on the floor, I can hit it with a hammer. It won't break, but it's not going to get any better. It doesn't care. You can hit it, you can throw it, you can do anything with it. Robustness doesn't care one way or another. It's still going to be a bar of titanium. So then what's antifragile? What's the exact opposite? The polar opposite of fragility is something that actually gets better. So when you stress it out, instead of breaking, it gets stronger. So I have a tree here. Why do I have a tree? Are you guys familiar with the concept of the biodome? Scientists came up with this idea of creating this kind of perfect place of nature where you have every plant and different animals and kind of create a perfect area where you can grow anything and keep things alive. And it's really, really a cool concept. But what they noticed is they planted all these plants and these trees, and they watched them grow, and they were patting themselves on the back. And the trees would get to a certain size, and then they'd completely fall over. What's wrong with our biodome? And they looked, and the root system on these trees didn't exist. It was just tiny. So they got to a certain size, and the trees just fell over because they had no roots. Why was that? The scientists forgot to reproduce wind. The trees did not have stressors within their environment. And without wind stressing the tree out, it didn't send the right communication to grow out the root system. So trees are anti-fragile. They improve with stress. The wind trying to blow them over as seedlings, that communicates growth. It tells them to get stronger. Instead of breaking it like a teacup, it actually makes it stronger. This concept of anti-fragility is really interesting. Thanksgiving, I got this little injury. We had all the family come over. We usually do, and I love to cook. So I cooked this big meal. And I've never really cut myself before, but I had a cousin of mine, and he wanted to help out. So I said, okay, we need to rough chop some tomatoes. And so he started to slice the tomatoes. And I was like, oh no, hold on, let me show you the rough chop really quick. So I just go over to the station, and I'm barely paying attention. I'm like, here's a rough chop. And luckily it wasn't too bad. But this injury shows anti-fragility. How does it show anti-fragility? Well, first of all, if I was a fragile system, then what would happen is I'd cut my thumb and I'd be out. I'd be in the bed, unable to cook, 500 air. If I was a robust system, I would cut my thumb, bleed over everything and just keep going. I wouldn't care one way or another. It wouldn't do anything for me. So what makes it anti-fragile? What makes it anti-fragile is that I learned. I have a much deeper respect for Japanese knives than I've ever had before. And I'm much less likely in the future to make this mistake. I have a deeper respect and appreciation for how much damage these can cause. And so I've learned. I'm a system, and by damaging my thumb, I've learned to improve. So I've strengthened with this small injury. So it's, the concept of anti-fragility is one that you can use in all sorts of ways. It's super fascinating. I'll give you one last example and we'll move on. This one is really interesting. Is jobs can be fragile, robust, or anti-fragile. So, for example, my wife, she does a little part-time work. So she works for a kitchen company that sells stuff. So she's a sales associate. Sales associate jobs are very fragile. What happens with a sales associate job? You have to be very careful with what you say. If you go up to a customer and they insult you, you have to smile. You have to be very, you cannot say the wrong thing. And if you punch that customer in the face, you lose your job instantly. So it's a very fragile job. What is an example of a robust job? A robust job would be somebody like a bouncer. A bouncer can punch somebody in the face every night, multiple times a night. Does it make his job better? No. He doesn't get a raise for punching people in the face, but he doesn't get fired. That's part of his job. It's a very robust job. But there are actually anti-fragile jobs as well. And that's fascinating too. Being an artist or an author is an anti-fragile job. What do I mean by that? Well, if you write a book and then you go and punch somebody in the face, you might get covered in the New York Times. And then you'll sell lots of books. So it's actually the stressors and the craziness, things that are random, that could other people could lose their jobs, that make being an author a more successful job. So it's something that you can apply to lots of different ways and thinking. It's a very interesting concept, but it's also a concept that I haven't seen applied to IT very much. But I think it does have lots of really interesting, useful applications. So what are some examples of fragile characteristics of application development with today? So if you look at web application architectures, if you find a web application or if you've built one that's sluggish, locked in, monolithic, tightly coupled, heavyweight, complicated, and doesn't have redundancy, chances are you have built a fragile application. Chances are your application is going to not scale well. It's going to hit problems when there's actual usage. Just this last Black Friday, there was a big outage with Best Buy. And I feel really bad because that's the one time that you do not want your website to go down, and it did. Unfortunately, I can't say for sure, but they probably had a fragile web application architecture. What are some characteristics of anti-fragility within IT? Agility. Even agile web development is a characteristic of anti-fragility. Interoperability, decentralization, loosely coupling, lightweight, simple, with lots of redundancy. These are the characteristics that you look for in an anti-fragile web architecture. These are things that show that things can grow in strength under stress. So there's actually a fantastic example of things that grow under stress in one of the best cloud companies out there right now. It's a very well-known example. It's the Chaos Monkey. So Netflix, they actually enforce chaos and randomness. They have this thing called a chaos monkey that actively randomly kills its own servers. So they go around trying to break things. And they try to break things at 4 a.m. They try to break things on Thanksgiving. They all the time, these chaos monkeys are going. And to anybody who's been a software developer and building web applications, this might sound like a nightmare. It might sound like your worst nightmare. But in fact, wouldn't you rather see things break before Black Friday? Wouldn't it be better to see that? And maybe if Best Buy had been load testing their systems, maybe not in kind of a perfect biodome environment, but if they had been load testing while having a chaos monkey that was trying to shut things down at the same time, it might have reproduced a more chaotic system, and they might have seen a fragile system at work. So web architectures are changing. And we see this happening at the large scale. We see Twitters and Facebooks growing up right in front of our face. We don't see the whales showing up. We don't see crashing Twitters as much anymore. And that's because they have shifted from heavy monolithic systems where they had N-tier layered cakes, and they've started decoupling them. And what's interesting is that the industry is also moving so that instead of starting out with layer cakes and eventually decoupling them, software development is going towards a system where you start out with lightweight distributed share-nothing systems. Excuse me. So instead of going to these models after the fact, after things are breaking, people are thinking about them more and more upfront. Shifting more and more to microservices, shifting more and more to taking big monoliths and making lots of smaller applications that speak to each other through APIs and communicate through things like message buses and queues, have asynchronous processes. So all of that is shifting, and so that's what we're going to talk about a little bit more today. Sorry. So if this is the legacy web architecture, if this is the layer cake view, what does the more modern view look like? What is the architecture shifting towards? At the center of the more modern architecture system for web architectures is a message bus, or a distributed service discovery, key value store, something that can help all of the loosely coupled systems communicate with each other. This can be lots of different kinds of technologies. It ranges in the Docker world with containers. A very popular system here is called etcd, from the people who made CoreOS, which is a minimalized operating system. The most popular part of this CoreOS project is the etcd project, and it's a service discovery system that's decentralized, and that's very, very important, because the last thing you want in kind of this new model is to have the entire architecture be centered around a message bus that is on one server, and if that server crashes, the entire thing can't talk to each other and falls apart. So the concepts of distributed service discovery, distributed key value stores, so that all of these different components can talk to each other is very important. It can be, in some cases, it can be much more simple technology. It might be something like Mongo database or a Redis queue. And but anything that can basically stitch together all of these lightweight systems. So instead of layering them on top of each other, you're now stitching them together in a much more distributed fashion. The other aspect of this is that there's a lot more smaller pieces. So instead of building your application code in one database and in one code base, you're now building smaller systems that are more functional and specifically built for one purpose. So before, you might build your user registration system within your application code and it's all bundled together. In more modern web architectures, a user authentication system could be its own application, and all it does is it's responsible for owning the user database, and it has lightly coupled interactions with everything else. So authentication happens within one application, and maybe blogging happens within a different application. Different functionalities become more specialized, and they talk to each other through standard REST APIs. The other interesting thing about that is that instead of having one large database with everything, each specialized application that is much smaller and more functional will have its own databases. So the user database for the user authentication application might be, you might realize, oh, I can use MySQL for that. But then another database might scale faster and may be a much bigger database. So you might realize you need to use something, a NoSQL database, a Mongo database. And you have that flexibility of choice. So when you decouple your system, you can scale the pieces independently. You have more flexibility about how you scale the pieces. You have more choice. And those systems can work together in unison. Where if you kill any piece of it, if you have a chaos monkey, it's not going to kill the entire system. And in fact, one of the common patterns in this kind of design is one of the kinds of applications within modern web architectures is a health manager. And that health manager its job is to watch the state of the service system and say, okay, how many application servers are there? How are the database servers? How's the health of everything looking? And when it notices that half your application servers are gone, it'll send the message to go spin up some more. So coming up with these concepts of specializing and making smaller applications that do less but have but can talk to each other is really key. Background tasks, Hadoop systems, they can all be stitched together. So the whole idea is stitching together highly functional, simpler units scales a lot better because functionally this is a much more resilient, anti-fragile system. Now, I wanted to just make a note here is that the system itself, to be anti-fragile, it to some extent is anti-fragile on its own, but the system doesn't work without people also learning from it. So to move it from just being a resilient system to an anti-fragile system, it's part of the operations, the DevOps, the programmer's job to make sure that there aren't choke points. Because even if you have a microservices architecture where these services are more specialized, you can still have choke points. You can still design your way into a corner, which is why Netflix has this chaos monkey. They're designing a contract that says, I know that you as the software developer might make code that is fragile, but the contract is you try not to, and if you ever do, you're going to get called out on it early. The idea of agile software development is that you don't want to have to wait 6 months, 9 months to figure out where your bugs are or what features to build next. And if you take that concept of agility into operations, you get things like the chaos monkey. You get to break it early. instead of waiting for Black Friday. So I hope that makes sense. We'll have questions and time for you guys to ask questions and dig into some details during the break. But I wanted to start talking about the 6 worst web practices and how to avoid them. Because, again, just because you are implementing in a more modern way and doing microservices and thinking about anti-fragility up front doesn't mean you can't get things wrong. So there's lots of pitfalls, lots of ways that you can still have trouble. And I wanted to cover a few of them. What's the first bad practice that I see? Synchronicity. If you've seen this I Love Lucy episode, it's a great one. They're in a chocolate factory, and they're trying to wrap individual chocolates, and the conveyor belt's moving, and they get behind and start stuffing chocolate in their face. It's I think it's this episode's actually on Amazon Instant Video, so if you haven't seen it, you definitely should. But 3-tier systems are like these synchronous chocolate factories. Information comes in, the browser request comes in, it goes through your cake, all the way down, gathers information from the database and brings it all the way back up, presents it in HTML to the browser. So they're like factory lines. And if any one part of the factory line chokes, if you have a Lucy in your factory line, it falls apart. The whole thing falls apart. You have to push the emergency button, line stops. So this leads to complexity. It leads to building monoliths. So the whole idea of the factory line is that you're building monolithic code. You're putting all of your information into one stack. Now, I'm going to be talking about building factory lines in a different context in the future, because there's nothing wrong fundamentally with factory lines. It's where you put them that's important. Having them while you are deploying your code is a fantastic place to have a factory line. We'll talk about that in a little bit, but having them as a real-time part of trying to deliver information to a customer through the web browser, that's a terrible idea. So synchronicity is one of the first bad practices. The second one is dependency on file systems. This is the one that's very tricky. It's a very, very difficult one to find. And if you haven't written code for platform as a service before, you might not be familiar with this concept, but with platform as a service like Heroku, for example, they don't give you access to the file system. So you can't write stuff to the file system. So they actually enforce at the application layer this concept in order to prevent you from making this bad practice. But in a lot of other platforms as a service, if you're doing it like, if you're building an application on OpenShift or on Cloud Foundry, then you do have the ability to write to the file system. Why is that a bad thing? The state data doesn't replicate easily. And so this is one of those places that as you need to have multiple copies of your application as it scales out, as it scales horizontally, if you've stored data on one instance of your application and you're trying to load up a whole bunch of other ones, they're not going to have the same data. So the browser request comes in. If it hits one with one piece of data and one that doesn't have it, you're going to get inconsistencies and it's going to start to fall apart. So how do people usually deal with this? They usually deal with this by saying, oh, that's not a problem. I'll just add NFS. I'll just add a back-end file system that shares the information between all my application servers. And that works up until a point. But there's lots of problems with that. Gluster is another technology that's often used. But these kinds of technologies that share a file system are usually very chatty, and more importantly, they're choke points. So they are places that they will scale up to a point, just like the database. They'll work great when you just get it up and starting at a small layer, but as you're getting larger and larger, they're going to be one of the places that keeps getting slower, that eventually breaks, and it's very complex. Lots of network traffic. And when you architect that way, you're architecting yourself into a monolith. The monolith in this case, if you're writing to a file system, is the file system. And it gets you thinking about, it's a crutch. It's a crutch that lets you keep doing things the way you're kind of used to doing things. And so dependency on file systems is one of the biggest hidden things. So if you're going back and you're trying to figure out, how do I move my application to the cloud? How do I think about cloud architectures? This is one place where doing a very deep audit is very, very important. If you are in a factory line environment, the third worst practice is doing a lot of heavy server-side processing. This made sense when the web was early. In the mid-90s, when I started coding, servers were much more powerful than desktop computers. Desktop computers were slow, browsers were really slow, there was very little RAM, and there was very little functionality you could do client-side. And so you did a lot of the heavy lifting on your server side and presented all the HTML, everything just exactly right before it reached the client. That made sense then, but the clients have changed dramatically. The browsers have changed. They're much more fast. The clients have much more capabilities. And so what has that done? It's shifted the processing to happen from server side, where you're generating all of your HTML up front, to client side. Client side processing, where you're processing the data not on the application servers themselves. The application server's job becomes to serve the data, the raw data, and compiling that data into a visual format becomes a client's operation. So there's a whole bunch of new technologies to make this easier and easier. There's web frameworks. There's things like Backbone and Ember that do a better and better job of doing heavy lifting for you on the client side within the browser, composing the data so that your server-side functionality becomes much more limited. So instead of on the server side having complex templates that you're using to generate all your HTML architecturally just right with everything listed before it's sent up to the client, now the server-side processing becomes a lot smaller. You're getting rid of your HTML templates within the server side. And on the server side, they're now sending JSON formatted data. So the server side's job is to give data to the client. And the client's job is to make sure that it looks right on the web browser. And one of the really nice things about this is what it does for mobile. Because a lot of times, increasingly, we're talking about more mobile-first development. And what do you need when you're dealing with mobile applications are APIs. You need the data. The mobile client's job is to compose that data into something for consumption. And so you're not generating HTML for mobile consumption. So you need APIs in the first place. And in a mobile app situation, that makes a lot of sense because you often have a native application. But in a web environment, that concept is shifting so that the web environment is starting to act more like a mobile client. The web side, instead of being just handed all the HTML, Like WordPress will generate the HTML before it's just exactly right and then hand it to the browser. It's shifting towards this concept of the clients are API driven. And this is how Twitter scaled as well. In fact, there was a point in time where Twitter was exclusively using its own APIs, and the client the website was all API driven. They've shifted back towards generating HTML before they send it to the web browser. However, the generation still happens at a different layer. So they still have microservices that are responsible for the APIs generating the data, but now the HTML generation is its own microservice. So thinking about separating the tasks and either having the client deal with it or other microservices presenting the content in different formats is a big trend. Another bad practice is expecting services to always be available, designing for success instead of designing for failure. The companies like Netflix are showing that designing for failure up front is such an important radical concept. Trying to break it instead of trying to prove that that the code works as expected. That's kind of the concept of continuous integration and using unit tests is to make sure that the code does what you thought it was supposed to do. So I needed the web application to send this list of user data in this action. So I'll write my unit test and I'll make sure that, oh yes, it did send the right data as expected. This concept is to make sure that things are designed for failure. So why is this important? Well, first, it's important because in cloud environments especially, the cloud has lots of failure. And so this is a really interesting concept. Services like Amazon, they tell you that their servers are bound to fail. And that's actually just an architectural principle that you're supposed to design around. So they don't say that this is like a bug. It is now just an architecture feature that you can't rely on instances and servers to stay alive. So if you're on cloud environments, there's a high probability that they could just stop working. So you have to be thinking about those kinds of concepts before you even go into them. Designing for failure and designing for disaster is important. A lot of times the disaster recovery systems that I've seen are really slow and prone to error. They're architected separately from the design and architecture of the web application themselves. And people rarely test them. They might never do a fire drill, or even they might do a fire drill once a year. If you start shifting your thinking and thinking of more like Netflix, more like a chaos monkey, and trying to induce problems and errors as you're going, you're going to be creating a more resilient, anti-fragile system. So inducing errors is a way, and the idea is to induce small errors. It's to cut your thumb every once in a while, to remind you how sharp the blade is. It's to design that up front, and that knowing that that's going to make you stronger in the long run. Talking about cloud, another bad practice that I see, and I've seen this many, many times, is moving to the cloud without a plan. So I've seen many large companies come and say, we're migrating to the cloud. We need a migration plan. We're coming up with a migration plan. And even CenturyLink, the company I work for right now, is doing this internally. We are shifting into the cloud more and more. We have our own CenturyLink cloud, and so internally we're thinking how do we get more workloads onto it. And often this is thought of and kind of presented as a cost reduction. Well, it's cheaper for us to go on the cloud. It's cheaper for us to think of things that way. But this is a lot trickier than it looks up front for a number of reasons. Now, first of all, depending on how you're calculating costs, some of you might know this dirty little secret, but at large scale, moving to the cloud is not cheaper. It's actually, it can be a lot more expensive. It's depending on your scale, of course, but you know, one of the biggest benefits is supposed to be a cost reduction. But if you do this blindly, and if you say, okay, we're just going to wholesale move into the cloud, anybody who's actually done that can warn you that that's not necessarily cheaper, and it could be a lot more expensive. There are things like the higher failure rates for servers that you have to architect into your applications. So this is another big pitfall that I see a lot of companies going into, is they think that they can take legacy web architectures, those 3-tier systems, the N-tier systems, even a lot of single server systems. You know, what I've seen is that in a lot of cases, they'll have a company will have single server applications where they have the database and the web application all in one server, and that's actually worked fine for them because it's been on dedicated hardware, or maybe it's dedicated hardware virtualized on premise, and they've never had outages, or they have very rare outages. So having single server applications works just great for them. And so they think, okay, we're going to migrate this all into the cloud. And so we're going to take this virtual machine that has our database and application, we're just going to put it in the cloud, and it'll be cheaper. Now, first of all, it might not be cheaper. Second of all, that's a terrible practice, because the robustness and resilience of a dedicated server does not translate to cloud servers. Cloud servers can and do go down very frequently. And even if you architect a system where the servers themselves, like maybe you've architected it so that it's distributed as N-tier, so if one server goes down, it doesn't all go down. Even data centers can go down. We've seen this with large storms and hurricanes. Entire data centers can go down with the cloud. And so there's all these risks inherent in cloud migration that aren't always thought about. So migrations are a great time to plan for modeling costs, but they're also a great time to really do an audit and see, is it time for us to start thinking about more modern architectures for the applications? So instead of just saying, let's migrate because we have a mandate to migrate, it's also a time to look back and say, is it time to not just update, or is not just time to migrate, but is also time to rethink and spruce up some of the architectures that we've had in the past. Lack of redundancy. This is a big one. Single points of failure is the last of the bad practices. There's plenty more bad practices, but these 6 really stand out that I've seen many, many times. Lack of redundancy. These single points of failure are always the one-eyed monsters that get you. And there are so many places that you can have single points of failure. And it's very, very important that you be looking for them. Your DNS could be a single point of failure. Load balancers. So you might have lots of application servers behind a load balancer, but then you don't have redundancy of your load balancers. I've seen networks that don't have any redundancy, so they've done a perfect job. They have multiple load balancers, they have lots of application servers, they have this decoupled system all on one network. So single points of failure are, and lack of redundancy, usually lack of redundancy comes from thinking about minimizing costs. That makes sense. But what are you trading off? You're trading the robustness and your minimizing your costs is also making a fragile application. So that might make sense if your application is never going to scale, but it's certainly not a good practice. So choke points are a big place that you should put a lot of focus looking for them. And this is one of the places where the Netflix system of actively killing things points out choke points very quickly. Because when you're just destroying servers and trying to break things, when things do break, when there is a catastrophe and the whole system does fall down, that gives you an opportunity to check in and see why did our system fail. Look for those the choke points are always going to be where systems had the big failures, and so this will point them out very quickly. So if those are the places that that don't work that you should look out for, what should you do instead? So instead of synchronous processes, we should be thinking about asynchronous processes. So the microservices concepts, small decoupled applications, focused applications that just do what they are designed to build very, very well, and thinking about specializing applications. So instead of monolithic applications where all of the code is all within one code base, think about creating systems that collaborate with each other. Each thing should do one thing very, 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 very well and scale very, very well. So REST APIs are very much a standard within microservices. There used to be SOAP APIs and XML RPC. All that has shifted. It's all gone towards REST. REST is kind of won the API game. And so JSON and REST are the areas that you should focus on. Message buses are a really great way to have those intercommunicate. And we'll get into what message buses architectures look like in just a minute. Distributed object storage. So instead of writing files to disk, you should be thinking about Memcache, Redis, MongoDB, CouchDB, NoSQL systems. One of the really tricky areas that can get you tripped up when you're thinking about disks is sessions. A lot of time, if you're using PHP, for example, sometimes Ruby without Ruby on Rails, sessions are actually stored on the disk too. And if you're not careful, you might have a user, as you scale out your application, a user could come into your web app once, log in. The next time they come in, they're logged out. You're like, what happened? It seems broken. What you did is you forgot that your sessions were on the disk, and you need to be thinking of all of those places on the disk and moving them into distributed object storage. And it's very important when you do distributed object storage that it is actually distributed. So I've seen lots of cases where people use something like Memcache for sessions, but they only have one Memcache server. There's a choke point. So setting up distribution, setting up redundancy for the distributed object storage is very important. Caching is a great way to get extra use. So if you don't need that much data for session storage, you can reuse the same Memcache and Redis system for caching data and keeping it available so that you're not hitting your database as well. So distributed object storage, NoSQL is a must in modern web architectures. Microservices. So leveraging the client side. Angular, Ember, Backbone. If you've heard of these technologies but haven't tried them yet, they're really built to take advantage of JSON REST APIs. So if you're, instead of building applications that generate HTML, if you're generating applications that write JSON REST APIs, Angular and Ember and Backbone can consume them for you and send them into, create the web look and feel for your application very quickly. So it's a very agile, very quick way to use APIs effectively. And if you're thinking about writing REST APIs, on the back end, there's lots of frameworks that can help you do that too. So if you're going from large monolithic and you're thinking more small micro frameworks, there's now specialized frameworks within every programming language for building smaller applications. So in Java, Spring, Spark, Jersey. In Ruby, Sinatra was the first micro framework, and it was built in order for people to write simpler web applications. They saw Ruby on Rails, and Ruby on Rails is almost proud of having batteries included. It's proud to have all the bells and whistles that you need, all the form functions built into it, so that you can build your perfect web application to start with. Sinatra came as a response to Ruby on Rails, and it said, all that complication, that's great, but I just want to build APIs. So Sinatra was built to really help you build JSON REST APIs with the least amount of code, and that's inspired a lot of other frameworks, and every programming language out there has them. The bonus is that now you can power your mobile applications because you're writing the APIs anyhow. So now your APIs can be consumed in lots of different formats. So microservices that interact through APIs are a very good practice. The nice thing about these things as well, if you've never written an application for Platform as a Service, these applications do very, very well in Platform as a Service, which is not always the case. If you're trying to deploy WordPress or Drupal or Joomla content management systems kind of wholesale into Platform as a Service, depending on which one, you might actually have to do, you might have to do a lot of research. Because they have disk dependencies, so some of them might not work out of the box. You might have to configure them differently. The database kind of works a little differently. So a lot of times you have to do a lot of tweaking to get kind of a larger monolithic application onto a cloud PaaS type of environment. Microservices, they don't use file systems. They're much smaller, compact. These are perfectly tuned for PaaS-like environments, cloud-like environments. They're a lot easier to scale, and they're built for that kind of environment where none of them are going to be huge, but each of them is responsible for one thing really well. Architecting for failure, proactively stress your system. Stressing the system should be considered healthy. Trying to break it should encourage strength. It's kind of it's not terribly intuitive, but this is especially true the more you're thinking about cloud, the more you're thinking about going into the cloud, the more you proactively stress and create crazy environments where you never expected. That's where you're going to learn where your choke points are. That's where you're going to learn how to create systems that scale well. So make all failures an opportunity. Just like I did with my thumb, make them an opportunity to learn. Instead of a failure being something that you're, get fired over or upset about or have a big trouble over, that should be a moment of rejoicing. Now we have learned something that we can institutionalize. We can create a better, more scalable, faster, more resilient application than ever. Prepare for the unexpected. Use cloud migration as an opportunity to modernize architecture. So this is one of the best things you can do is instead of just saying we're going to move into the cloud for cost reduction, don't have to it. Don't just say I'm going to, okay, all I need to do is take all of our virtual machine templates from on-prem and import to Amazon and we're done. That's the worst thing you can do. Because not applications do well in cloud environments. So using it as an opportunity to do an audit, using it as an opportunity to find choke points, using it as an opportunity to eliminate disk dependencies and state dependencies is incredibly important. Automation is very important to cloud architectures. So using it as an opportunity to increase the automation and not just reduce cost is a really great practice. Redundancy everywhere. A lot of people, they think that, okay, so what's redundancy mean? Well, okay, instead of one Memcache server, I'm going to have 2. Or maybe I'll have 3. I don't know if you guys know the Hydra story, Greek, that's what that monster is. When you cut off one head of Hydra, 2 pop up in its place. And if you start thinking that way about your own redundancy, 2 or 3 Memcache servers, what happens, Google's rule of thumb is 5. Because if they have 2 or 3, if one goes down, it could quickly overload. It could create a Titanic situation. So that the 2 that are left are now overtaxed. And they fall over because there's too much taxing going on there. So Google's rule of thumb is for 5x redundancy. And so thinking about redundancy in that way, it doesn't necessarily make sense from a cost perspective, bottom line perspective. It absolutely makes sense if you want to stay up on Black Friday. Getting the most from the cloud. So I wanted to talk a little bit about the portfolio of cloud services available. So much has been happening within the developer community, developer tools, SaaS and cloud services have been popping up so quickly that it's sometimes hard and you might not realize everything that's available to you. So I wanted to just do a very quick overview about some of the services available as a developer. Developer tools, infrastructure as a service tools, DevOps and orchestration tools. So I'll do a quick overview of that. And then I want to talk a little bit about orchestration. Because I think orchestration is one of the new kinds of technology trends that you're going to hear more and more about. And so I want to talk to you about what that means because it can be, if you don't know what that means very well up front, it can be a new concept. And then we'll go to the conclusion. So no matter what kind of, so if you're thinking about microservices, there's all sorts of different kinds of things where you don't actually need to build them yourself. So if you're thinking about microservices and you're saying, okay, logging should be a microservice. Aggregating the logs from all of my, all those microservice applications, maybe that can be its own microservice. You don't necessarily need to build your own microservice in a microservices architecture. You can actually leverage SaaS services built for developer tools in order to not have to build them yourself. This doesn't always make sense. In some cases, obviously there's proprietary information that can't go off-premise. There's all sorts of concerns, but if you're not dealing with credit card information, or if it's something that does have a little bit more flexibility. There's all sorts of cloud managed services available to developers today that didn't exist when I started programming. So if it's logging, email, background tasks, because even a queuing system, maybe you haven't done queuing systems before or you're not familiar with them, you don't have to learn how to run them yourself. You can use third-party services like Iron.io. Search can be a managed service. So all of these different components, you can use third parties to build out functionality. And it's really important because when you're not architecting a monolith, you have this flexibility. You can say, do I need to build this microservice, or do I outsource it to a third party? It is important, however, to think about the consequences up front. A lot of people don't realize that there are certainly trade-offs. Obviously, you don't have to be managing the microservices yourself if you're going with a third party like this. But if you're doing something like ClearDB, which does hosted MySQL for you, so it's a way that you don't have to do MySQL. They'll manage it, run it for you. There are some concerns that you might have and you should be thinking about before you commit to going with them. So concerns like, at what point does it not make sense for me to be on this ClearDB service for MySQL anymore? And what does that mean? What happens when I outgrow them? What happens when my database gets too big and ClearDB doesn't have a tier for me, or the performance isn't what I hoped for, or all of those kinds of questions? Before you kind of swipe your credit card and forget about it, you have to be thinking about it and planning for it and architecting for it. So there's a lot to choose from, and I think that the slides are already going to be distributed, so you guys can already use this list as a starting point. But do think about your plans for services that are kind of very key to you. So using an email service, you might never need to not use something like SendGrid. SendGrid might scale perfectly well. Millions of emails a day is perfectly fine for SendGrid. But making sure that you understand how the costs grow and what the limitations for each one of these microservices is very important. For infrastructure and platform as a service, there's also an increasing variety for you to choose from every single day. Amazon, Google, Azure, DigitalOcean is a new infrastructure as a service provider. They specialize in cheaper SSD-backed servers. So you can get an SSD cloud server in 30 seconds for like $5 a month with DigitalOcean, which is pretty cool. The downside is they don't have any of the kind of on-top services that Amazon has. So like all the Elastic Beanstalk stuff, everything, the 50-plus services that Amazon has on top of their cloud offering, DigitalOcean doesn't have any. It just has the virtual machines. But DigitalOcean is doing a really good job hosting Docker containers, and we'll get into that as well. CenturyLink Cloud has a more enterprise-friendly cloud, and we focus, for us, our customers are more enterprise than something like Amazon. Amazon deals with a lot of independent developers. CenturyLink deals with large businesses, Thomson Reuters, Coke, large enterprises, and so we have different constraints. So for us, it's not acceptable for instances of a server to go down. Architecting that was one of the key differences. We didn't want people to have to worry that the server instances could disappear at a whim. Performance, disk I/O was very important to us. So each cloud kind of has a different angle and has different functionality. There's a lot of choices for platform as a service too. They have open source and proprietary. So with Heroku, it's a hosted service to deploy your applications. Very easy to use, but it's all proprietary. So you can never run Heroku on your own, and you can never go off of their system. Something like Cloud Foundry and OpenShift, those are open source. And in fact, AppFog was my platform as a service. It's part of CenturyLink now. When I built it, I didn't build it. I built it before Cloud Foundry had come out, was released. There was no open source platform as a service. But when Cloud Foundry came out, I noticed that it was really advanced in some ways, and my system was really advanced in other ways. So I decided to embrace Cloud Foundry. So I took the Cloud Foundry code base, added the stuff that we had advanced in platform as a service, and built AppFog on top of Cloud Foundry. So I'm a big fan of what they're doing at Cloud Foundry. Google App Engine has been around for quite a while, and they've done some. They've been increasingly iterating. They're doing a lot of stuff around Docker recently, which I think is really cool. And obviously, Windows Azure is also one of the leaders. So a lot of choices there. DevOps and orchestration. With DevOps and orchestration, the DevOps tooling you might be familiar with, you have lots of choices. Chef, Puppet, SaltStack is a little newer. Ansible is a little newer. Zookeeper does some stuff too. It's a little bit more complicated. And those are really great for automating operations. So then what's orchestration? Specifically, there's different kinds of orchestration, and orchestration can mean different things in different contexts. So one type of orchestration might be something like OpenStack orchestrates the infrastructure as a service. But I'm not talking about that kind. I'm not talking about virtual machine orchestration. I'm talking more about DevOps orchestration. So how does that differ? Well, if DevOps is things like Chef and Puppet, if you haven't used those tools, what they do is they allow you to declaratively configure a server. So you, instead of going in and modifying your Apache configuration manually and tweaking and installing different packages all by hand, something like Chef or Puppet will, you tell it in a script. You declare, I want these packages installed, and I want this configured that way and this way. And Chef and Puppet's job is to do all the work. So that way, once you have your declaration, and they're in the form of recipes or cookbooks, you can send that declaration to a whole bunch of servers, and they will all replicate the same, run the same tasks, and have be very similar. So DevOps adds that ability to declaratively set up servers. Orchestration, in the context of DevOps, what that does is it allows you to declaratively set up kind of the microservices environment of multiple applications. So it's kind of a meta declarative on top of DevOps. And I'll get into that in just a little bit right now. So I love this metaphor for describing what orchestration is. So when's the last time Internet Explorer asked you to choose which CPU you want to run your web browser on? Never. Why? Because Internet Explorer decides on its own. The CPU functionality, the multiple cores, you never have to worry about it. The computer figures out where is the best core to run Internet Explorer for you. So then why, if computers are smart enough to pick a core, why are we still trying to decide which virtual machine we should put our Ruby on Rails app on? That's what orchestration fundamentally does. Orchestration helps you decide where to put your workloads, whether they are application workloads or database workloads. Manually deciding where they go and how to set them up and how they communicate with each other is becoming an antiquated thing. Orchestration chooses the CPU for you. So it's API-driven automation. It's built on top of DevOps tools. So it uses and embraces DevOps tools and functionality to declaratively deploy complex cloud applications. So if Chef lets you declaratively set up an individual server, orchestration will let you declaratively deploy a complex cloud application. So when you saw those slides earlier where we're now having microservices, which means instead of one application, we've got 6 or a dozen, you might think to yourself, oh boy, like just setting this up is going to be a nightmare. Managing it, restarting it, deploying it, maintaining it. As they become more complex, they add resiliency and robustness and scalability, but that makes them harder to manage. And so now orchestration allows you to declaratively set these processes up. So before orchestration, the kind of architecture diagram, your application would be sending tasks to a job scheduling engine, which would have a bunch of workers. So this might be a Hadoop system, or it could be an email sending process, something that takes a lot of time. So your application was kind of sending asynchronous requests to a whole pool of job workers. This was kind of the standard for how to do long-running processes in legacy web architectures. So if you have the layer cake, this is how you would do things that took longer than a single request was going to take. Orchestration is shifting that. So now, instead of the application being the most important part, and that sends requests to your job scheduling engine, it raises the job scheduling engine up to first-class status. Now your job scheduling engine deploys your application. The application isn't sending the requests to the job scheduling engine. And to talk to the job scheduling engine, you now do it declaratively. So right here we've got an example from Kubernetes. And Kubernetes actually uses Zookeeper. So Mesos uses Zookeeper. So if you're using the Mesos orchestration system, underneath the Mesos orchestration, which gives you a declarative format, Zookeeper is kind of executing the commands underneath the covers. So this format here, this declarative format, is one for the Kubernetes project, which just came out of Google. It's been in the news a lot. You might have heard about it. This is essentially what it does. Here you've got an example where you have a Redis service that you're declaratively setting up. You're saying, here's my Redis service. Here's the Docker container that has the logic for my Redis service. Here's the ports. That way, the system itself can know how different services interact with each other. So in the microservices architecture, where you have lots of small services, each one communicates on a different port. They have to know which IP. The orchestration system is set up to connect those things together for you. So you declare what you want. The job scheduling engine takes the declaration and does all the work of setting up as many application servers as it needs. It has a built-in queue, message bus. And in fact, as you're building your application, if you wanted to use a message bus in your architecture, you can actually use, if you're using an orchestration, depending on which one, you can actually use the orchestration's layer's message bus. So if you were thinking about going into this direction and incorporating distributed microservice architecture on a message bus already, Going that next level and looking into orchestration could be a great way to get that piece of the puzzle, but also be able to manage these larger systems in a more automated way. So the orchestration is really built to declaratively manage larger, more complicated, anti-fragile systems, robust systems that can scale. In fact, the Mesos project, which is a form of orchestration, that was actually used to scale Twitter. So when Twitter was having all of its whale fails, and they needed to get into a system that was more distributed, that was more scalable, they used Mesos orchestration to help them get there. And it's been proven for tens of thousands of servers. And instead of having system administrators that are managing tens of thousands of servers, they're using Mesos to automate that instead. So it's something that Kubernetes is a newer one from Google. It's less tested. It's kind of moving quickly. And in the Mesos world, there's, just as a side note, if you're going to get into it, there's different layers as well. The Mesos project is very low level. And so as a developer, you might not be interacting with it directly, unless you want the message bus functionality. Where you would actually go is Mesosphere, which kind of manages. It's almost like a vSphere for the orchestration. And that has more APIs that are developer friendly. And then there's, even on top of Mesosphere, is a thing called Marathon. And Marathon is the most developer friendly. So it's kind of going from very low level to more abstract. And so the Marathon project is the one, that's where you would actually say, here's my application code, go deploy it. And it will go through and do the right things within Marathon and Mesos to set up your environment. And so the Marathon is the one that's most like the Kubernetes project from Google. And then there's newer ones like the CoreOS system, which I mentioned earlier, is more Docker and container oriented. And CoreOS has its own orchestration system called Fleet. And so they've been building a thing called Fleet, which also does orchestration. And I know this is getting a little complicated, but Docker themselves is actually also building their own orchestration. So I think that orchestration is increasingly important in today's modern web architecture. And it's very quickly moving, so I wanted to help try to explain these difficult concepts in these pictures. So now we've done it. We've gotten to the point where anybody that's asleep can now wake up. And so if you see a buddy, you can just nudge them. I'm going to give you the 3 things to remember. So we've done a lot of talking. I want to leave you guys with 3 things to remember, and then we'll answer a few questions. The first conclusion, legacy web architectures are fragile. Layer cakes. They break. Even though N-tier used to be kind of the stamped seal of approval, best way to kind of architect a web application, they are no longer the best practice. They're fragile, they break. Number 2, a lot of people, a lot of savvy architects of web applications, they know not to focus on scalability too soon. It's called premature optimization. And the idea is that if you prematurely optimize, you might be optimizing the wrong way. You might be setting up systems that don't make sense because maybe at that point that you don't know how the application is going to scale. I completely agree with that concept. And I totally agree that you shouldn't prematurely optimize for scaling. But I think it's very important to think about anti-fragility as early as possible. I think anti-fragility is a more core concept than scalability. and it's something that I don't think there is an early enough time that you can start thinking about anti-fragility. That you can't be prematurely anti-fragile. So I think that's very important to think about anti-fragility up front. Number 3, microservices are the future. Big monolithic applications used to be torn apart when they needed to scale. That's changing. We're now seeing a world where from day one we're building microservices that interact with each other. Lightweight, distributed, share nothing, REST, JSON, APIs. That's where things are going. That's a modern web architecture. Orchestration is being developed to make those easier to deploy. And that's all I'd like you guys to remember from today's talk. So in the next section, we'll be talking about the future of web application architectures and where things are going, what's coming next. We'll get more into Docker. I'll spend a good amount of time explaining what Docker is, why it's important, and how you can think about it, incorporating it into your application development life cycles. But I'll pause here to see. We have about 5 minutes for questions, and then we'll go take a break. And in the break, you can come up to me and ask me questions as well. Are there any? Great. So the question is, how do you deal with siloed data in enterprise situations where the data is stuck and that's a fantastic problem for microservices. When you have data that's stuck, building small services that are very specifically built around a certain data set to do a specific functionality is actually much, it's well suited for a microservices architecture because you can run those on-premise right near the data and be able to take advantage of lower latency, higher speed. And if the microservices architecture is set up so that there are some services that run right near the data and they have APIs that can talk to other services, that's really well, a microservices architecture runs really well within siloed data systems. In fact, as I mentioned, in microservices architecture, a lot of times the services themselves have their own data stores. So if you didn't have siloed data before, you're actually creating siloed data intentionally with microservices because each microservice can have its own data set and data store, and they can be different ones. You can scale. One might work really well with a Redis backend. One might need an Oracle backend. And in a monolithic database, that might be a problem because now you have all these database drivers and dependencies. But if in a microservices one, you can easily have a microservice dedicated to an Oracle backend that has nothing to do with a different microservice that talks to MySQL. Does that answer the question? Yeah. Or is there more specific follow-up? Yeah, that one's much more specific to the question is how do you combine the data from different microservices? That is a problem that is much more, there isn't necessarily best practices as much as case-by-case basis, depending on what kind of, that one becomes a lot more fractal in the answers.
What methodology do you look at these different products and how you integrate them? How do you assess them? And how do you see them when you pick a particular one? Some of them don't have enough critical mass in the market, so they'll wither on the vine. If you chose that product, all of a sudden you're at a dead end. You're having to migrate a fundamental framework piece out of that product into something that's living still. So
Yes.
how do you approach the analysis of all these products and their integration?
Yeah, that's a great question. So there's two parts to that, because there's the technology that is like, do I pick Mongo or Couch? There's technology within the architectures themselves. But then the question that you might be asking as well is the architectures themselves. What orchestration system do you pick? Which platform as a service? Which infrastructure as a service do you pick? And I think that what's really interesting is in a microservices approach, you are hedging your bets. Because it's not a monolith, and because you are focusing on the right tool for a certain purpose, if you make the wrong bet for which database backend you pick, maybe Mongo looked really good, and you didn't realize that at scale it had some read-write random latency issues. When you have a microservices architecture and the Mongo database is encapsulated within a smaller subsection of your application architecture, it actually becomes a lot easier to migrate into a different alternative because you haven't bet the farm on one piece of technology. And then at the larger scale, which orchestration do you pick? Which Kubernetes or Mesos, or which infrastructures and services do you pick? The nice thing about approaching it from a microservices perspective is that you actually have gains there too. Because the code you're writing is, because it's smaller and more encapsulated, there's less chance for it to have a lot of lock-in. So each service that you're building is fundamentally simpler than a large monolithic application that's going to have all sorts of requirements and is tied into it's a lot easier to decouple a smaller system than it is a bigger system. And so when you're architecting your applications in these smaller siloed ways, then the orchestration pick matters less as well. So if you're asking about right now in this moment, the safest bet in orchestration necessarily is Mesos, because they're the ones that have the most scale. But the thing that should reduce your fears of dependency lock-in is that if you write your application architectures to Mesos, it's significantly less difficult to migrate it to something like Kubernetes later, simply because you have been already working within microservices. Kind of save you both ways. They save you on the underlying implementation, and they make it easier on the overlying because there's less lock-in.
We have about 15 minutes till the next session. I wanted to make sure that folks were aware we have some light snacks outside. So feel free to go and enjoy that. You're welcome to ask Lucas questions up front as well. Please try to be back and seated by about noon so that we can start our next session on time. Thanks. Hi, welcome back, everyone. We're about to begin the second session of the day. For those joining, again, thank you very much for your time. I appreciate taking the time out of your day to sort of contribute to your learning here. We had a few questions about whether or not the slides would be sent out, and we will send those out after the meeting, so we'll get those to you. These sessions will also be available as recordings. So if you were unable to attend the first session, you'll be able to see that as a recording, and we'll distribute that information a little bit later. So with that, I'll turn it back to Lucas for the second session.
Thank you so much. In this half, we're going to talk about the future of web applications. So the first half, we talked about where have things gone and where are we today. What are the trends that have brought us to and why do we think about things the way we think about them now? But now we're going to look to the future. Where are things going? So we're going to look at some trends. We're going to look at what the future holds. But before I go into that, I want to give people a little bit more information about myself because you guys might have been here the whole time. The people online might just be joining, so I want to give a little introduction to myself. I'd like to tell you a little bit about how I got into programming. So around 1996, I was in middle school when I got into programming. In elementary school, I'd done some basic and played around with my Commodore 64, but it was in middle school that I discovered the World Wide Web. And I still remember the day that I took my index.html file and first figured out how to get my credentials into FTP and put that file on. And when I typed in the web address, I remember realizing that anything I typed into this could be read by anybody else in the world. And at that point, I was just completely hooked. I'd totally fallen in love with the idea of the web. And so at the time, I used to do card magic. I used to be a magician. And so I thought, what am I going to do with this? I can write anything, so what will I write? So I decided to make a web page that was for magicians. And so the idea would be you'd have to pass a test in order to get into the website. And once you pass the test, so I know you're a magician, you can see all the tricks and learn all the secrets. And so I'd collect tricks from other magicians and centralize the repository. And at the time, the web was so early, there was pretty much no other magic website like this, a community-driven website. And I'd built it with PHP. So it was one of the most popular websites that dealt with magic for quite a while, quite amount of time. And I did it through high school and I got into college. It was interesting because I went from just a simple application. I bought some dedicated servers. I got some co-location facilities. It was really fun for me. It was a big hobby that I would build this up and cultivate, and it became pretty highly trafficked. And I remember the day in college when I woke up and I went in to check the website and the page wouldn't load. And I refreshed and it wouldn't load. And so I call up my dedicated server provider and what's going on here? And they said, well, it looks like your computers have had some hard drive failure. And so for years I had been maintaining this system and growing it, and I built it out to be a multi-server system, and the disks failed. And I'd broken rule number 0. Rule number 1, I had no backups, no offsite backups. And so my passion that got me into programming in the first place, the website was lost. So all the tricks were lost. And it still makes me sad. It was one of the things that drove me to build a platform as a service. In platform as a service, a lot of the tasks of setting up your infrastructure, of managing it, of doing backups, all of those things are automated for you. So you write the code, you build your system, and the platform as a service, it takes over that functionality for you. So if I had been running my own website in a platform as a service, the backups would be automated, the scale out would be automated. So it was really out of my own experiences that I brought with me the idea of what can platform as a service do for other programmers. So what's this talk about? The future. We're going to talk about what's next for web application architectures. We're going to talk about how to future-proof applications with microservices. So we're going to go deeper into microservices. Then we'll talk about 6 insider technology trends. These are the 6 things that I think are going to be the future. They're going to be where technology is in a year and 2 and 3 years from now. We've talked about a few of them. We haven't talked about some of the others. but we'll go into a little bit more depth. And then we're going to focus in on Docker, and we're going to spend a good amount of time explaining what Docker is, because I think, I'll give you just a preview, the number one insider trend is Docker. I think Docker is going to change and revolutionize the way we think about applications going forward. So I'm going to spend a good chunk of time giving you guys the basics, because Docker is actually not complicated. Not a lot of people know how to use it, but that doesn't mean that it's complicated. There are complicated technologies. Orchestration technologies are not easy. Docker is easy. So I'm going to show you how to use Docker. That's going to be some time that I also spend talking about security. Docker changes how you think about security. And understanding that early is a competitive advantage, because very few people right now are taking advantage of Docker. And even the ones that are, there's a lot of confusion around what's going on with security. So I'm going to spend some time talking about that as well. And just like the first talk, at the end, if you'd taken a little nap, that's okay, because I will give you the 3 things that you need to remember, so don't worry. What's next for web application architectures? Where is it all going? There's a famous quote from Mark Andreessen that software is eating the world. And I totally think that that trend is super true, but I think that within the software world, automation is eating the world. All of the meta trend of everything that we've been talking about, if we look at it from kind of bird's eye view, the meta trend is that everything is becoming more automated. DevOps is creating more automation for the operations, so that there's less manual system administration. We're getting more and more declarative instead of manual. So automation is eating the software world. We're getting more and more automated in more and more places. Web architectures are shifting. They're shifting from the heavy monolithic backend systems to the lightweight distributed share-nothing systems. So as they shift, one of the questions that came up in the last talk, what's a share-nothing architecture? I just want to spend a little bit of time in case anybody is not familiar with this concept, because it's very important. A share-nothing infrastructure architecture is one where there's no persistent state stored on the disk. So in legacy architectures, you might keep state around. You might upload files. So if it's a web application where you share a picture or you're uploading some personal documents, a lot of times those used to be stored on the disk that ran the application itself. But that's a big problem, and I'll tell you why in a second. But when you do share nothing, it's easy to scale. Share nothing architectures don't share that data at the file system layer. Uploaded files, sessions, they all go into object storage, distributed object storage. What happens when you don't do share nothing? When you don't do share nothing, you end up with 404s, because the content that's uploaded on one application server is not available on another one, and so what happens is an inconsistent behavior, and the system breaks. If you're logged in at one point in time and the session is on the disk, you're not going to see that session at a different point in time, so it'll feel like you're logged out. So share nothing architectures are fundamentally ones that don't share state. State is one of the biggest problems for web application architectures. And I haven't seen any significant shifts in technology to solve those problems. The existing solutions, the NFS, the clusters, are kludgy and don't scale to massive scale. And so the answer that is becoming more and more resonant is, instead of trying to share information at the disk layer, don't share it at all. So a share nothing architecture doesn't share in the disk. Web architectures are also changing from hands-on, deployed and managed, to automated. DevOps is automating the operations. It's bringing developers and operations closer together. And there's multiple ways that we see deployments being more and more automated. We see it through platform as a service, which can take your code and do all of the deployment for you automatically. But we also see it through continuous integration and continuous deployment technologies. So web architectures are improving in not only their structure, becoming more decentralized, more share nothing, but they're also becoming easier to deploy on a continual basis. And one of the foundations of a great agile workflow is that the testing process isn't something that happens as a separate process. Rather, it's continuously being tested. That the unit tests are continuously being run. Every time you change anything within your code base, the entire suite of code is being tested. And so at any point in time, instead of waiting till a certain period of time passes, you're always testing your code. So automation is entering more and more parts of the software development lifecycle. It's like a factory line. Now, we mentioned factory lines as being a bad thing earlier. And in a synchronous process where somebody wants to log into a website and get their information, a factory line is a terrible way to do that because any break in the factory line will break the entire process. But a factory line is actually turns out to be a great way to test, build, and deploy software. So in those kinds of situations, there isn't that kind of real-time problem of the user needs information back as quickly as possible. Rather, you need a factory to deploy your application. And before, there were many, many steps. And in kind of a traditional enterprise IT environment, the developers wouldn't even be involved in the deployment process. They'd write their code. Maybe they test it on their laptop. They pull up their browser to make sure it works there. And then they hand it off. They might FTP it to a server, and the IT team will pick it up and do their magic. That process is all becoming automated. It's turning into a factory line. And there's all sorts of technologies to help you with that. So then how do you future-proof applications? How do you make sure that you don't get stuck picking the wrong technology? You don't get stuck if you're trying to become more modern, but you don't know which technology to pick yet and which one's going to win. How do you make sure that you're doing the best practices with your microservices? I'm going to talk about 4 things today. I'm going to talk about the REST APIs more. I'm going to talk about asset hosting, session management, and asynchronous processes. But I talk about more in the book. So the book that is on the table in front of you is Programming for Platform as a Service. Because I've seen lots of people trying to move applications into a platform as a service and more modern, futuristic deployment methods. And I've seen them fail in lots of ways. And so the book, I have 1 chapter about legacy applications and 1 chapter about greenfield. So if you're trying to think about what should you think about when you're dealing with legacy applications, trying to get them into a cloud-like environment and a more automated environment. There's a set of things that you need to look into. And if you're dealing with building a brand new application and you don't have the constraints of legacy applications, there's other things. But today we'll just talk about 4 things. So JSON REST APIs. The JSON REST APIs is kind of a more verbose way of saying a microservice. A microservice is an increasing trend within the developer community for creating smaller, lightweight services. And those services are pieces of code that develop APIs. They communicate with databases to produce JSON formatted data, and they present that data through APIs. So encapsulating different pieces, like we talked about in the first one, but if you weren't in the first talk, the whole idea is that if you have something like a user authentication or a blog post service or a credit card processing service, instead of having them all in one monolithic logical grouping, if each one of those is its own application and specializes on its own thing. And so one of the interesting things is if you start separating those things, for example, credit card processing has a lot of restrictions. But those restrictions not necessarily apply to a blog posting part of your application. So you're able, if you separate your application logic into these different capsules, you can implement different security processes for them. And that way, the credit card services can be PCI compliant, and the blog post service, maybe that lives in the cloud. Maybe that part is hosted on a cloud infrastructure and the credit card services are on-premise, but they can communicate with each other in a distributed, loosely coupled way to work together. So thinking more along these lines, it used to be the standards were more around SOAP and XML RPC. That's shifted towards more REST APIs and JSON formatted data instead of XML formatted data. And so that's the first place to look. Asset hosting. Using object storage, using CDNs. There's a whole new set of cloud CDNs that are more developer friendly than they used to be. Something like CloudFront is a great tool from Amazon that gives you kind of an instant CDN out of your object storage. And Cloudflare is a third-party CDN that allows you to speed up your asset hosting. Really developer-friendly tools that can kind of encapsulate certain areas of your application services without having to wholesale move into a different environment. So thinking about asset hosting as the foundation of your share nothing architecture, having object storage being a way to allow you to scale horizontally is really important. Session management. Sessions are very tricky in the cloud. So especially when you're dealing with something that is kind of a pre-baked application, a content management system, WordPress, Joomla, Drupal, these kinds of systems, the session management can get really tricky. So when you're trying to scale it out, the cookies and sessions often break a share nothing architecture. So a lot of times there are hosting companies that do WordPress hosting for you, and what they will do is they'll actually set up NFS systems to do a disk persistence. So in some content management systems, sometimes the only way to scale them effectively is to implement these disk persistence because there's so much it is already a monolith, and it's difficult to decompose it because it wasn't necessarily built to run in cloud environments. But there are plugins, and increasingly you see different ways. These frameworks are moving closer and closer to share-nothing architectures, but they're not there yet. So thinking about sessions, and depending on the kind of workloads, this can be a big gotcha. Asynchronous processes, simple queuing services like Redis can be used for making sure that background tasks are run on separate systems. But orchestration makes queuing systems a first-class citizen. So if you ever want to make asynchronous processes more built into your architectures, orchestration, thinking about putting orchestration into your system might be a way for you to not only bring in better queuing architectures, but also give you more functionality as well. So again, there's more in the book, and we get into more specific examples in the book, and I point out some of the plugins that you can use for WordPress and Joomla and Drupal. So you don't have to be lost if you find yourself managing these frameworks. So what are the 6 insider tech trends in cloud computing? I already gave away the first one. Linux containers are revolutionizing infrastructure. It's interesting because Docker didn't exist 2 years ago. It's less than 2 years old. It is the fastest growing open source project in history. It's gone from just being developed and in beta to being used by tens of thousands of developers around the world in just a few months. The online repository for Docker is full of images. So what Docker does is it makes Linux containers a lot easier to use. So Linux containers and BSD jails, they've been around for 10 years. Solaris zones, these aren't new things. What Docker did is it gave a very, very simple API for using them and sharing them with others. So when you're using Docker, you can create Linux containers that have your code, that have your services, that have your microservices within the container, and then you can put them into a repository. And this repository, it's kind of like GitHub. So the Docker Hub is very much like GitHub for infrastructure. In fact, this is the part that makes Docker that much different and so special. A lot of people see Docker and they're like, what's the point? Who cares? The thing that is so important about Docker is not the Linux container management part of Docker. It's the social collaborative part of Docker. The fact that you can share containers, that I can, on one computer, create a container, and on another computer, reproduce the exact same system, that's what changes everything. And I'll show you an example of that soon. Number 2, I don't think you'll be surprised, is orchestration. So we've got a number of players in this space. CoreOS has their fleet. Mesos, used by Twitter, Kubernetes from Google. And it seems like there's more and more orchestrations coming out of the woodworks every day. Different companies have already been developing them. And so I think you'll see more of these. Declarative DevOps automation for cloud apps. So the whole idea with orchestration is that as systems become more distributed and yet also at the same time more automated, you need smarter technology to manage the deployments. You need systems that can decide without your intervention where to deploy applications based on rules. So if there are applications that are data specific, there should be rules that say that the application workloads should be launched on the same infrastructure as the data. So you can have those kinds of systems set up with orchestration. You can have the rules declaratively set up so that applications that are necessary to stay near their workloads do so, and the ones that don't. So you can also create rules for bursting. So you can have orchestration that's set up to work both on-premise and in cloud environments. So the orchestrator itself could know that there's some workloads that can go onto the cloud and some that can't. And it can deploy those. It can watch the system. It can look for certain things, CPU, RAM, disk, and it can scale for you on your behalf. So orchestration is something that is very quickly moving. It's a very, very big tech trend that I think we're going to see more and more of in the coming years. I think that if I had been giving this talk to you guys a few years ago, we'd be focusing on a big tech trend of things like NoSQL databases. At this point, NoSQL databases are very well established. We kind of have the big players out there. There's not a lot of new stuff popping up, so it's still a big trend, but it's a much more established trend. Orchestration is kind of at the same point now that NoSQL databases were a few years ago. The third big tech trend that I see happening within technology today, especially for developers, is the continuous integration and deployment stuff going on. So automation for source control is super interesting, and obviously there's things like Jenkins and Circle and Travis. These are some of the bigger automation for continuous integration services. So what they will do is they will take your code, they'll do all the compilation, all the testing, and they will deploy it for you. So continuous integration has been a little bit more established, but is still a growing trend. We see more and more of these services happening, popping up. So Travis and Circle are some of the hosted services. Jenkins is an open source project that you can run on your own. You can run it on premise. And it's interesting, I think that this trend becomes even more important as containerization becomes more widely adopted. Why is that? With continuous integration, you take code that is in your source control, and it does all the testing, and it deploys it to production. So that sounds great, and so you're adding automation. So what's the problem? The problem is that the code that you write on your laptop is clearly not the same environment as a production environment. Like if you're on a Mac, you're going to have different libraries. It's not even a Linux environment. And if you're deploying to a Linux environment or a RHEL system, not only are there differences in the environments, but just the whole way it's set up could be vastly different. So the way that the database is set up could be different. And there's all sorts of sneaky little hidden things so that what worked perfectly on the laptop just falls apart in production. That changes. That changes drastically with the adoption of something like Docker and Linux containers. Because when you are developing on your local machine within a Dockerized, containerized environment, you're actually, it is encapsulated the exact same environment that's going to go into production. So we're going to talk a lot more about that. I'm going to show you some architecture diagrams. But when you combine Docker with continuous integration, you're actually encapsulating the same state. So you can actually test and have more certainty that your continuous integration workflow is going to create more persistently good results. The fourth big trend that I keep seeing is micro everything. Microservices that we've talked about already. Micro frameworks. So there are all sorts of frameworks for creating microservices. As I mentioned in the previous talk, Ruby's Sinatra inspired a lot of these. Minimalized frameworks for doing small codes systems. Instead of creating fully blown out systems that have MVC architectures, you can even think smaller. You don't need to have model view controller when it's a simple REST API. And so if you bring it down even further, micro frameworks are exploding. There's more and more of them. Every language has them. .NET has them. Java has lots of them. But there are even micro languages coming out. So you can see this trend happening. Go is a new programming language that's come out from Google. And it's really interesting. It's kind of a successor to something like C++. But what it can do is you can compile binaries. It feels more like a dynamic language when you're writing it, but it's all compiled down to a static binary. And that's very important for security. So remember about Go when I go back into security in a little bit. Hack is a version of PHP where they're adding more types into PHP. So PHP traditionally wasn't a very strongly typed system; it was very loosely typed. Hack adds type, which allows you to have speed. It comes out of Facebook, and so you see there are different attempts to take programming languages, try to make them compile into smaller, compile into faster binaries. Things like Sinatra for micro frameworks are inspiring a lot of innovation for programming languages, and everything is shifting towards micro. Mobile is a trend, and I keep it in this list for myself because unlike something like NoSQL, which I think is a trend that is sort of plateauing, we kind of see it having matured, I don't think that mobile is anywhere close to plateau. The way that mobile is going, we're still at the tip of the iceberg. There's many multiples of growth that are still going to happen within mobile. Even though it's such a big thing today, it's in 5-10 years, it is going to be many multiples bigger deal than it is today. So I think this is a growing trend. The nice thing is that microservices already have the same philosophy for powering mobile applications because they provide APIs that can be consumed by mobile applications. And so things that support mobile application development, the services that allow you to do push notifications, these things are a growing trend. I think there's going to be increasing focus on mobile. The sixth big trend is client-side JavaScript. There's more and more logic happening in the browser. And in the previous talk, we talked about Angular and Backbone and Ember, but increasingly we're starting to see people thinking about the web browser almost like a desktop environment. So we're seeing a number of things like CoffeeScript coming and building out all sorts of widgets where instead of designing HTML for your web application, you're getting heavier client-side JavaScript, where you think about the web application a lot like you do a desktop application. So you think about composing widgets together the way you might do it in Xcode, or the way you might think about designing more of the kind of desktop-y approaches. So there's more and more of these tools popping up that widgetize the whole web experience, and they're all powered by APIs. So client-side JavaScript is getting faster, more robust. There are more and more JavaScript libraries, and we're going to see that trend continuing. So now I want to spend a little bit of time talking about how to get the most from Docker and Linux containers. And also, once we understand what Docker is and what Linux containers are, I want to go in and talk a little bit about the security aspects that Docker uses, and the way you can use them to change the way you think about security. So what is Docker? One of the big kind of metaphors in the Docker ecosystem, the world of Docker, is to think about containers, shipping containers. So Linux containers are like shipping containers. And before 1960, if you were shipping a bunch of stuff, you just throw it on a boat. And there was not a lot of standardization. There were lots of types of things that you can put on a boat. And there's lots of types of ways that you can transport stuff. So it might be a boat, it might be a truck. And before 1960, it was a total mess. The shipping container changed that. It was a piece of technology that fundamentally changed the way that we moved goods. It created a standard that we created a whole set of tools around. So with the shipping container, we could standardize trucks to a certain size. We could standardize the ships to a certain size. We could standardize the cranes to a certain size. And no matter what we were shipping, as long as it fit inside of a shipping container, all of the equipment built around it would work. So what does that mean? How does that transfer to the Docker analogy? Right now, it seems like you think about like the shipping container, the pre-shipping container. How did they not come up with this concept of a standard size of a shipping container? It seems so obvious to us now. But before Docker, we were in the same position like pre-1960 world. And today, we're still in that same situation. We have all sorts of different kinds of code and services. We have MySQL databases, we have Oracle databases, we have Ruby on Rails applications that are full of dynamic code. We have Java applications, we have Go applications, which are static binaries, and they're all different sizes, they all require different things. And we don't have any containers. All we do is we stick them all onto servers. We say, okay, let's put all the goods into the server, and you know, that is the kind of standard logic that we're using today. Docker changes that fundamentally. Docker gives us the containers to put our code into. That gives us the containers to put our services into. So you can put MySQL into a container. And what happens is that once it's in a container, it can run on any server exactly the same way. It's protected from everything else. There's no interactions. And so you have consistency and you have reproducibility with Docker containers. the containerization model is very different than the virtual machine model. With containers, they're isolated, but they share the same Linux kernel. So every containerized application has a different disk, and you can get root on one container and you don't have root on another. But they all share the same kernel. So with virtual machines, you have complete isolation. Even though you have multiple virtual machines on a single box, they don't share anything. So they have their own kernel, they have their own binaries. With containers, you can have a lot more of them on a server. So they're a lot lighter weight. Since they share the kernel, they don't require as many resources. So on a typical server let's say you have a server that could do 10 virtual machines, and that's kind of like the max. You could easily do 100 or 1,000 Linux containers because they're much lighter weight. They don't require as much RAM. They don't require their own kernel. And so you can spin them up, and you can spin them up in microseconds. In a fraction of a second, you can have a container up and running. So they're much faster, they're much more agile, and they're reproducible. The kind of architecturally, the way to think about the basics of a Docker system is that you have a Docker engine, and that's responsible for launching the containers themselves. So the Docker engine has the responsibility to manage the Linux containers. Originally, the management was for LXC on Linux, but they've expanded their support, and now they're able to support lots of different things. They have a new project called libcontainer, which is based in Go, and the idea is to abstract it away so that they can have manage other kinds of containers. So in theory, you can manage BSD jails and Solaris zones just as easily as you can Linux containers. And in fact, that abstraction is how Microsoft recently announced that they're going to support Docker within a Windows environment, because clearly you can't be running Linux containers in a Windows because they're different operating systems, and fundamentally they share the kernel. But because you have this abstraction, Microsoft is building a similar type of thing that will talk through the API of libcontainer, so that fundamentally to Docker it looks like you just have more containers. On the same host that has the Docker engine, you have a Docker container image registry. So the image registry is a really interesting thing because it's a decoupled system. It's a distributed system. Every Docker engine has its own Docker container image repository. And you can, so on my laptop, I'll have mine. On your laptop, you'll have yours. We can share Docker images through this container image registry, and you can actually create public registries. So Docker has their own canonical public registry of containers. And you can create your own, and you can publicize it. But even if you don't publicize it, you still have one running. It's just not published, available to others, but it's still running on your machine. So when you want to run a containerized MySQL, you say Docker run MySQL, it will pull a MySQL container from the Docker image registry into your local image registry. Once the Docker container's in your local image registry, you'll be able to run it. And then you have a Docker client. So the Docker engine right now has to be on Linux. So this is a problem until Microsoft finishes their integration. The Docker engine has to be running on Linux. And But you can still have it on a Mac. So what happens on a Mac is you just need to virtualize Linux machines. And so there's an installer at docker.com, makes it very, very easy. It's all bundled. And once you install the package, it includes VirtualBox, which will do Oracle's free open source virtualization technology. And it will spin up a Linux machine to run your Docker engine on your Mac. The Docker client speaks to the Docker engine through an API. And the Docker client has is a native binary that can run on any system. The Docker client's written in Go. And with Go, you can compile it to pretty much any operating system, any architecture, processor architecture. So they've decoupled the client and the server so that you can run the Docker client natively, and it can pass through to talk to your hosted virtual Linux image on your Mac to be able to have, it feels like you have a native Docker even though you're actually running a virtual machine. So you can create your own Docker images, or you can pull them in from Docker image repositories. So what does it look like? So Docker is very easy to use, as I mentioned. Docker is a very simple tool, even though a lot of people still haven't used it yet. So let me show you an example of doing something simple like echoing hello world without Docker. So what does echoing hello world look like with Docker? Docker run Ubuntu echo hello world. So if you've never run Docker before, that's as easy as it is. What does that do? So the Docker command, if you're on a Linux box, might be on the same machine that the Docker engine is on. If it's not, if you're on a Mac, then that will be posting to the Docker engine on the virtual machine on your Mac. Ubuntu is obviously the operating system that you're going to be running it on. So it runs an Ubuntu container. One of the interesting things is even though the Docker container shares the Linux kernel, it doesn't share the operating system. So you can actually do any Linux-based operating system in any container. So if I wanted to run Echo Hello World in CentOS, I can run Docker run CentOS Echo Hello World. If I wanted to run it in Fedora or in Gentoo, you can run any kind of operating system, any Linux operating system within a container. And what will happen is Docker run, if you don't have the image itself, it will go to the canonical repository, or if you specify your own repository, it will look at there. And it will look and say, okay, we need an Ubuntu, we need a Fedora. It will pull the image, and it'll run whatever command you ask it to. So when you run Echo Hello World, it'll just bring you back to your shell prompt, and it'll be over with. But you can actually create an interactive Docker session as well. So if you add a couple flags to your Docker run command, it will make it interactive. So this is a way for you to create a Docker container, go into it, and start running stuff. In fact, one of the ways you can create customized containers is you can Docker run -i-t Ubuntu bash. Then you have root prompt. You can go ahead and configure your container exactly how you want it. You can manually go in, apt-get install MySQL, you can tune it, you can put in Oracle, you can put your license in for any kind of software, bundle it in, create your container just like you want it. And once you've finished playing with your container, in a separate window, you can actually write Docker commit. So this is a lot like source control. git commit or SVN commit, you can actually commit your file system. And it will know everything you've installed within the Ubuntu or Gentoo or whatever. It'll know everything you've installed. It'll know the differences, and it'll keep a track of changes. So it's like a git commit for your file system itself. It's very lightweight. It happens in seconds. And then you can exit out of your Docker run and reproduce it. So instead of having to go and install all your binaries again, you can say Docker run, and instead of putting Ubuntu, you now put the hash. After you put Docker commit, it gives you a hash. Just like git commit creates a hash for every change in your code, Docker commit creates a hash. And so instead of running Docker run Ubuntu, you say Docker run and then put the hash. And now you've reproduced the exact container with all the changes, all the state encapsulated perfectly in less than a second. Very, very lightweight. So that's a way to do Docker interactively. It's very easy, and it's a really great way to get used to Docker and try to figure out and play with Docker. Once you've created your container and it's running Nginx or Apache just the way you want it to be run, you can daemonize it. So in this case, what I did is, instead of customizing the Ubuntu image, I said, I don't want to run bash. I don't want to run echo hello world. I want to run netcat. So I want to create a very simple network service. So nc -l-p. So it creates a netcat daemon that's just listening on port 80. It doesn't do anything, but it's a daemon. And instead of using the -it flag, if you use the -d flag, it will daemonize the system. So now that container will be running in the background, and you can see when you run Docker ps all of your running processes. So Docker's super easy to use. One of the things you might notice here is that the ports doesn't show anything. So I've daemonized this. It should be listing on port 80, but I didn't tell Docker to open up port 80. So first of all, I'll show you how to do that. First, to open up the port, all you have to do is tell Docker which port to open. And when you tell Docker which port to open, it will randomly assign a local port on the host machine that will map to the container's port. But you're starting to see some of the interesting things you can do around security. I'll go into this deeper. But if you don't tell Docker the ports to open, you're not, anything within that container is not exposed to the outside world. So it's a really interesting, sets the stage for some security ideas. The other interesting thing to notice here is the Ubuntu image tag. So you see that it doesn't just say Ubuntu. Even though I said Ubuntu in the run command, it says Ubuntu :latest. This is another great thing about using Docker, is just like in Git version control, you can tag different versions, and you can have version 2.1 of your source control, of your source code. You can tag infrastructure containers with Docker too. So because I didn't specify it, it defaulted to the :latest, but you can specify any version of Ubuntu going back. And you can tag different versions of Ubuntu. And you can, when you're creating your own containers, this is how you do it. You can tag your container code to a version number. And so tagging containers, just wanted to show you more and more Docker stuff is very much, it feels like Git. It's very, very strongly inspired by Git and version control. And it really takes version control and transfers it to a DevOps mentality. That's what's so cool. if you just think that Docker is a Linux container manager, you're missing this aspect of Docker, that Docker is like version control for DevOps. And it lets you collaborate. So it keeps a history. Every time you make a change on a container, it knows it. And you can commit and keep committing different changes, and it keeps the history of those changes. So the file system has a record that is auditable and trackable. And doing that on virtual machines, it absolutely can be done, but it's much harder. You have to install stuff. You have to put tripwire. You have to managing file system changes on virtual machines. It's a lot harder than it is on containers. So you can open ports on daemonized Docker containers, and at that point, that's like a service. It's a microservice. You can communicate to that port. You can specify, so if you don't want it running on port 49153, you can tell it on Docker command line that maybe you want that Docker container to actually be bound to port 80 on the machine itself. So port 80 on the machine will talk to that Docker container. All you have to do is run -p 80:80. So you specify the local port and the remote port. And then you can have a Docker image running daemonized, serving any port you want. So Docker's super easy to use. And using Docker commit is a great way to get started using Docker without having to learn anything else. But Docker files are very, very powerful. And these are the way that you actually should be building your containers. So could you go in and create all of the containers you need manually? Once you've tuned them exactly how you want them, then you share them with everybody in your organization? Yes, you can do that. That is not the best practice, and it's not the best idea. The better idea is to declaratively do it. So you can do it manually or declaratively, and to do it declaratively, use a Docker file. And so the Docker file is a way to specify exactly what you need to build any container. So I want to step you through. They're not very hard to build from Ubuntu. So any container can be imported as the import file for a Docker file. So once this is a Docker file that creates an Nginx container. If you wanted to then create a container based off the Nginx container and added some other functionality to that container, maybe you wanted a hardened Nginx, you could say from Nginx and then start from that point so they could inherit from each other. Then you apt-get, update, and install, so you can run any arbitrary command. So these commands, you might have run them manually. Here's where you can just say run and keep a track of that. In fact, these Docker files are now being put into the source control themselves. So you have your base directory that has your source code for your application. You can just stick a Docker file in that base directory so that the application knows how to build itself into a container. Add dot, under the two run commands, the add dot command, what that does is the dot takes the current working directory and it moves it into the Docker container file system. So that's a great way. So let's say you're building an application and you put the Docker file in the base directory of your application. And let's say it is the heavy JavaScript, heavy HTML static front end to your microservices backend. So this is the part of your application that consumes the APIs that you've built, the JSON REST APIs. And so it doesn't need to be a dynamic system. It's not Tomcat, it's not Ruby, it's not Node. it's all it is HTML and JavaScript. So you just need something really good at delivering HTML and JavaScript, so Nginx is great. You can add dot, and what that will do is put the current working directory into the container, into the place where Nginx is expecting to, the default place that Nginx looks for HTML code. Then you can explicitly tell it to expose port 80, and then you can put in the command that you need it to run. So you specify exactly the constraints of your container, and then you can run Docker build. So once you've created the Docker file inside the home directory of your source code, all you have to do is run Docker build. You give it a name. So in this case, I did -t for the name, and CardMagic's my handle. So CardMagic/Nginx, and then dot to specify the current directory. What that will do is it will go through and run all the commands in the Docker file. At the end, you have a fully built, self-contained Nginx container that will run exactly the same anywhere. So whether it's on my laptop, whether it's in an on-premise system it's all non-virtualized, or if it's on Amazon Web Services or on DigitalOcean, it is exactly the same code. It's the same version of the operating system. There's no differences. It's encapsulated everything. So you're not going to ever have to deal with different versions of Nginx, different versions of Tomcat, different versions of MySQL, because you've now encapsulated that into the application itself. And at the end, you can see the hash that was built out. So at this point, you can run CardMagic Nginx on the machine. And you can reproduce your container anywhere. But you can also go back and you can see that hash. It's the exact same thing if you run docker run 3b7a04. Same thing. So I've just given a tag name for that hash. But now I can run it anywhere. And I wanted to show you, if you're on your Mac, there's a utility. When you install Docker, it's a utility called boot to Docker. So if you're on a Linux host, if you run curl with the 0.0.0 address, it works perfectly because your Docker engine is on the same machine as your Docker client. On your Mac, the Docker engine is virtualized. So if you run 0.0.0, there's no port forwarding set up automatically, so you'd get nothing. So boot to Docker is a great utility. It comes default. When you install Docker through the docker.com website on your Mac, you get boot to Docker. You just put the boot to Docker IP, and that will generate the virtual machine's IP, but you use the same port, and it works just like that. So at that point, this is the magic for me. We've talked about it, but I wanted to show you the commands because it's just so simple. Docker push. There's so many things that Docker is like Git, and this is the most, to me, the transformative part for Docker is Docker push. Because at that point, I'm taking the local container that I built, customized on my Mac, exactly how I wanted it, and I push it into the Docker Central repository. And a few months ago, the Docker Central repository had 18,000 images. So there was 18,000 images created by by people using Docker, and were pushed into the Docker Hub. Now it's orders of magnitude bigger. And what that does is it allows people to socially collaborate on DevOps the way that GitHub allowed people to socially collaborate on source code. Before, source code collaboration was hard, cumbersome, and it was kind of behind the scenes. And GitHub kind of transformed that, made it much easier. It made it easier to collaborate with people around the world. Docker is doing that to the DevOps environment, because now people are working with each other. They're creating repositories and sharing best practices. One of the things for me is like the idea that if you could become an expert in something. So like you could become an expert in Hadoop, and it might take you, a while to learn all the ins and outs and to be able to tune Hadoop exactly to the way you need it, and use best practices and all the flags and all the options. Docker allows the smartest Hadoop people in the world to create the best Hadoop containers in the world, and to put best practices not just in a book, but in a container that I can reproduce on my machine. And so it allows you to take the concepts, the best practices, and tap into the knowledge of the larger world, and pull in that information, reproducing the exact environment that Hortonworks might use, that any person that is an expert, you can take their knowledge and reproduce those environments exactly just by Docker pulling or Docker run. So I think that is super transformative. I think this is why I think Docker is going to change the way we think about technology in the years, because this changes a lot of the game. Sharing your container doesn't need to just be in the public repository. So the public repository is actually open source. So you can, in fact, it's the repository itself is in containers. So you can pull a Docker repository container into your own environment and be able to host your own internal private Docker registries. So that way, is especially important for enterprises and government, where sure, that's great, Lucas. Oh, it's awesome that you can pull Hortonworks containers, but we're not going to push our government contracted container into some public GitHub Docker hub. That doesn't make any sense. In GitHub, GitHub source code is proprietary, and it's the system's proprietary. You can license it from GitHub and run it behind your firewall, but you have to pay them. With Docker Hub, the code is open source, so you can actually take it on your own and run your own system, which is really interesting. There are going to be productized offerings, both from Docker, but also ecosystem players for add-on services to make it even more resilient. But unlike GitHub, you can actually reproduce it yourself if you want to put the work in yourself, and create your own registries so that your own team, the Docker images you use within your own team, never leave your own area. So a couple of do's and don'ts. Docker is really new. It's moving very quickly. It is still, although it's maturing really rapidly, there are things that there's a funny apostrophe there. There are things you should do and things you should avoid. Containerizing your application code is a fantastic idea. The whole concept is that the logic that runs on your laptop should be exactly the same as the logic that runs in dev test, in QA, and production. instead of having different environments in all of those different parts of your application lifecycle, they should be exactly the same. You should be able to have verified authenticity that whatever runs in QA is exactly the same as production, and that's what Docker gives you. So containerizing your application code is great. By creating consistency. So we go back to the comment I made about continuous integration. There's already work being done to integrate Docker into every continuous integration system out there. So that instead of sending your code to a continuous integration system, you're actually sending your containers. And when they go in as containers, that way at every stage, they're being tested the exactly same way. And in fact, there are now some hosted services that are born with Docker. So Shippable is a hosted continuous integration service that is primarily developed for testing Docker containers, not any specific repository of code, but it was developed Docker container first. Drone is an open source project that's kind of like Jenkins for continuous integration, except it too was built for containers first. So we're seeing a lot of ecosystem growth around containerization and tools for containerization. eBay is using this for doing their code testing and their code releases. So it's stuff that's being done out in the wild. Things that you should avoid doing in the wild is things like databases, persistence issues. We've riled against them a number of times in this talk. They don't do well in containers yet. So you can run MySQL in containers. You can run Oracle in containers. Right now, it's not necessarily a good idea to do that. There are developing practices for how to do it. The reason it's not a good idea is that if you don't do anything, your Docker container, as soon as you exit out of it, loses all its state. So you have your MySQL running in a Docker container, and the container closes or the server crashes or whatever happens, and now you've lost your entire database. So how do you get around that? There's a few ways. One is, just like the -d flag created daemonization for Docker, there's a -v flag for volumes. So you can have external volumes within your Docker container. So you could you could have your MySQL database or your Oracle database on your host operating system available read-write to any container. If you put -v flag and then you varlib MySQL, that varlib MySQL will then be available within the Docker container itself. And any changes you make to the database running varlib MySQL, when you exit out of the container, will still be persisted to the host's disk. Which is okay, but remember we're building for failure, not for success. That assumes that the host is going to survive. And especially in a cloud environment, we can't make that assumption. So it hasn't really solved the underlying problem of how do you deal with persistent disk data for large databases. It doesn't make sense yet. There's also another technique that is around instead of having your data within the host operating system, you can actually create data containers where the container itself has nothing running on it, but is intended to simply be a container for holding information. So you can mount volumes. Instead of mounting it from your host container into any other container, you're mounting your volume from a storage container into any other container. So there's different techniques happening, and there are people that are trying to work on persistence problems within Docker. So there's a project called Flocker that what it's trying to do is trying to solve this problem by making those containers that are disk containers more portable, so that they can move between any hosted Docker system a lot easier. That way, if something goes down, or if you need to transfer, or if one of the host Docker machines has disk corruption issues or disk I/O issues, you could move that Docker container, the disk container, to a different system. But it's very early. It's really in kind of an R&D stage. It's far from a production stage. So there's lots of work. I think that the future in the next few years, remember, Docker is less than 2 years old, so there's a lot of maturing that needs to happen. So I think that we will see databases within Docker, and that's going to make things really interesting when we do that. But don't do it today. The other thing to not do is multi-tenancy. So the concept, the trade-off, Docker seems great, and up to this point it seems like, why wouldn't we be doing this? It makes a lot of sense. It's lighter weight. You can run more of them on a server. They're faster. They're shareable. Why wouldn't we want to do this? Well, let's talk about security for a little bit. So running multi-tenant containers is a bad idea. Why is it a bad idea? Is because you're sharing a Linux kernel, you now have, if there is a zero-day exploit on the Linux kernel, if there's any way that somebody on one container can exploit the kernel, they can, in theory, have access to any other container running on your system. So if you're running a multi-tenant container system, you're running the risk that somebody is able to break out of their container and into any other container. You don't have as much risk in a virtualized cloud environment because they don't share Linux kernels. So there's a much smaller attack vector footprint with virtual machines. That's why we don't hear about massive, large-scale security problems on Amazon, is because people have a lot more trouble breaking out of a virtual machine containers or model. With containers, there actually have been, so far as proof of concepts. So there's code out in the wild. It doesn't work in today's Docker. They patch it, but they have been examples of code that actually will break out of a container and give you access to others. So it's not only possible, but it's actually been shown that you can do this. And so there's some big things that you should be thinking about, especially around security for Dockerized containers. But it's not all as glim as it sounds, and especially the press likes to make a big deal about how insecure Docker is. It's not necessarily as glim as it sounds, for a few reasons. One is if you incorporate SE Linux, you can actually mitigate a lot of these risks. So if you properly incorporate SE Linux into your Docker host, you can make it so that every container has its own, is not only containerized, but it gets its own privileges. And so if there is a zero-day exploit on the Linux kernel, which does happen every so often, when they try to break out of the container, they do break out, but they can't do anything. So there is that layer of protection. Integrating SE Linux is given to you by default if you're using a RHEL-based Docker host. So Red Hat's been doing a great job of making it easier to integrate security policies into Docker. Atomic is also from Red Hat using the same SE Linux. So what's Atomic? Atomic is very similar to CoreOS. And what are both of those? This is where the security stuff for Docker gets really interesting. And this, I think, is something that is very practical and something that changes the game for how to think about security. So CoreOS and Atomic are new operating systems. And what they've done with these operating systems is they have basically stripped them bare. They've taken everything out. So there is no longer an apt-get. There's no longer a yum. There's no package management system. So if you get an Atomic operating system, you can't yum install anything. You can't update source code. You can't install MySQL on an Atomic system through a yum package management. They've taken away a lot of the built-in binaries. In CoreOS, they've gone even further. They've with CoreOS, they're more radically minimalizing the systems. And why are they doing that? Well, when you have Docker, and basically all these things, Atomic and CoreOS, what they say is all you need is Docker. When you have Docker, Docker can package anything. So you don't need to yum install MySQL because you can Docker pull MySQL. And so any binary that you would need, you can get from the Docker registry. And so the idea is if that's true, and it is, then why do you need any binaries on your host machine? So what that does is you're radically reducing the attack vectors on the host machine. So right now, CoreOS and Atomic, they both have bash installed in the host machine. But you could imagine, why do you need bash? If you this kind of thinking is to reduce the security footprint of your host operating systems. Both for security, but for performance as well. When you reduce the footprint, there's less things running. It runs with less RAM, so it's more efficient, saves you money, cost savings. It's faster. And so on the outside of your application, the host machine itself, it's almost as if it's a no operating system. We had operating systems before, and the operating systems, they came with stuff. A Mac OS X comes with iMovie and comes with Pages. It doesn't ask you if you need iMovie. We're heading towards a world where server operating systems don't have an operating system. It's a kernel and a kernel, Docker, and a few others. SE Linux, right? Because what's the point of everything else? The application, the code is where what you care about, especially in a server environment. So why would I have bash on my host operating system? So the bash exploit security bug that that came out recently. If you were running on a minimalized no operating system kind of environment, you wouldn't have to be worried about it because your security vector was minimalized. So that's a really interesting thing happening on the outside, but what about inside? Because even if you don't have bash on your host operating system, the containers themselves, that you're still basing your containers off of Ubuntu. So even though your host might not be Ubuntu and full of binaries that you don't need anymore, the container itself, we pulled it from Ubuntu, right? So it's got all the binaries that have been missing on the host. In fact, that's even worse because the container operating system is the one that your code's running in the first place. So that's the one you really care about. You can't even get to the host because you're containerized. And if you break out, SE Linux can make it so that you can't do anything. So what's the point of the host minimalizing? There's actually an answer to that, and that's where things get really interesting. Because instead of starting from the Ubuntu image to build your application, you can actually start from a thing called a Scratch image. What's a Scratch image? Scratch image is nothing. Zero. It's literally no operating system. So it's a container that has nothing on it. And that's only possible with Docker and thinking about things in a containerized model because of the shared kernel aspect. The shared Linux kernel allows you to have containers that have nothing in the file system, which isn't possible with virtual machines. So then what do you do with a Scratch container? Seems pretty useless. Well, this is where I gave you a little note, a little flag. I wanted to talk to you about Go and the importance of Go. Is that you can actually build applications, modern applications, without having to worry about kind of digging so deep that you're into the C++ realm. You can still have kind of a more modern, dynamic language inspired programming language, but compile it into a single binary. And what you can do is you can create binaries out of Go that are completely self-contained and put that binary in the Scratch image. And now you're running a container that has nothing but your application. So if you're building REST APIs using Go, compile them down to a single binary with no library dependencies, put them into a container, run it on a minimalized host operating system, you've dramatically reduced your security vectors. I think this is something I'm super passionate and excited about. It's something that hasn't been possible to even think about. You can't imagine it in a virtualized system because they don't share kernels. So when you have to have a kernel, it comes with all this other stuff. So then you still have some attack vectors at the networking level, but you've taken all of the kind of external attack vectors. You're not running an operating system, and on the outside you're barely running an operating system. So it fundamentally changes the security approach to building applications if you containerize in this model. You can use it obviously with compiling C and C++. It's a lot harder if you're thinking about something like a dynamic language like Ruby or PHP. And with Java, there's still a lot of dependencies, but if you have the flexibility of going greenfield, if you can start with something new, if you have more flexibility, it's a really interesting concept that there are people playing with right now, but it's still early, but it's a very promising concept. On the network side, there's a lot of possibilities with containers as well. This is less, this is even earlier than kind of the disk side of things. So the disk side of security is interesting. On the networking side, when you have containers, you have the ability to have rules for the network interactions between those containers in a very strict way. And it gives you some flexibility. And there's this pattern that's emerging within the Docker ecosystem that's called the ambassador pattern. What's the ambassador pattern? One of the biggest problems, one of the biggest pitfalls for running Dockerized applications is if you have two Docker hosts that are on separate servers and your application needs to be deployed on both of them. Like maybe one of them has your database, one has your application containers. The problem is, how do you get those containers to talk to each other? If you're running containers on the same host, on the same physical box, you can actually run a command. In the command line, you can run docker link, L-I-N-K. And what that will do is it will inform one box of the other's existence. And that way, it's in an environmental variable that you can pull the environmental variable, and your application code can dynamically use the environmental variable to point to a database or another service. So it's a very flexible way. You don't have to hard code anything. You're not putting in IP addresses. You're not even putting in ports, because it's all passed in through environmental variables. It's all randomized. And so the problem is you can't Docker link to a container on a different host. That's going to be fixed in the future. It's not fixed right now. It's one of the biggest problems in Docker. Because obviously anybody running Docker in a production system is going to run it on multiple hosts. You want to scale out. And so the figuring out how to connect containers dynamically across servers, there's lots of solutions out there right now. And one of them is called the ambassador pattern. And the ambassador pattern is interesting for a few reasons. One way that it's interesting is because it solves this problem. What it does is it's essentially a proxy. So the container itself, all it does is proxy network traffic. And what you do is you set up an ambassador on each machine. So each host gets an ambassador, and the ambassadors are linked together. And so what happens then is that you can Docker link to the ambassador on your host machine, and that gives you the connection to any other machine that has an ambassador. That's where the name ambassador comes from. And so it acts as a network proxy within a containerized model. So it solves that problem, and I think it's a somewhat elegant solution, although it's a little kludgy when you think, why should I have proxies everywhere? It's like a waste of proxies. All these network proxies everywhere. If I was in a traditional virtualized environment, I wouldn't need any proxies. So it seems like somewhat of a waste. And it would be, except that there's so much potential when you think about what you can do with a smart ambassador. So if it was a dumb ambassador, all it did was move network traffic from one place to another, then it would be pretty useless. But it doesn't need to be a dumb ambassador. It can be a smart ambassador. What are some examples of a smart ambassador? One thing you can do is you can enforce contracts. You can say, these are the only MySQL commands that we are going to allow pass through our network buffer. So instead of passively listening to network traffic, you can start actively listening. And so you can say this application code is only allowed to send selects to the database, no deletes. So you can actually start enforcing things at a network layer that create more protections between your applications, their services, and all of that. You can also do things like using that to centralize the network traffic itself. You can use it as a tap and send that information to a centralized logging system so that you have a centralized account of your network through the ambassadors, through the networking proxies, into a centralized logging system. There's all sorts of things you can do when you realize that if containers have to talk to each other through these proxies, now you can start using them in more productive ways and taking advantage of them. So I think the disk stuff is very interesting around containerization. The opportunities around what you can do around networking with security is super interesting around Docker. But again, that's really early. There's a lot of work to be done. There are companies working on networking solutions for Docker container stuff. So one project right now is called Weave, and they're doing some stuff around Docker and networking. And Docker themselves have networking and security tooling in their roadmap and timeline. So there's a lot of opportunity. I've just laid out a few advanced concepts of what might be coming around. But I think that these kinds of ideas could fundamentally change the way we approach security for technology. We've made it again, so we can nudge our partners to wake up, and I'll give you the 3 conclusions. Number 1, automation is dominating the future landscape of web architectures. Anything that is manual is becoming automated. So if you want to know what the future looks like, just take everything that right now is a manual process and imagine a computer doing it for you. Microservices are the future. I don't know if any of you have seen Big Hero 6, but my little 4-year-old just loved that movie. And in it, there's this kid who makes robots. And he's trying to get into a robot making school, and to do that he has to make a project to impress the professor. And what he does is instead of making a big robot that was super impressive, he made like 6 garbage cans full of tiny little robots. And he could control them all. So it was like millions of robots, and they were all like this big, and they could turn into any shape they wanted. That's where web technology is going. It's in loosely coupled, distributed services. We're seeing big monoliths falling apart. We're building out lightweight distributed systems, and loosely coupled APIs are at the foundation of them. Docker and Linux containers are the new way to package and distribute your application. They're changing the way that we think about services themselves. They're changing the way we think about security. And they're changing the way we think about cloud. Cloud, for years, has been dominated by the concept of virtual machines. Virtual machines, instead of dedicated servers that somebody racks and stacks themselves. Docker not only can be run on virtual machines, but it can be run on bare metal. And in fact, the popularization of Docker is driving people to reconsider bare metal. You know, a lot of the drive to the cloud was around the concept of virtual machines, but Docker doesn't care. It could be virtual machines or not virtual machines, and you don't need to virtualize with Docker anymore. And if you have a bare metal server that goes down in a Dockerized world, you can still manage that. The whole point of one of the big drivers for virtualization was that it automated the machines, but containerization automates them as well, and it provides a lot of value that going back to containers on bare metal is something that you might see as well. So I appreciate your time. Open to any questions. I'm sure there's lots of really interesting things that you can think about doing with Docker. So feel free to ask me anything and come up to me afterwards.
I have a question regarding running databases on Docker. Is it like I don't want to run a database for a transaction processing. let's say I have a legacy database in SQL 2005, and there are some legacy application which gives me running a complex query and gives me a result. Now I'm modernizing my IT, so I don't want to modernize that piece because it's been used once in a year or need basis only. So what I want to do is to build a Docker which first instantiates SQL 2005 and then restores the database, and then I run and I get that output. Then again, I just make that Docker go away.
Yes.
Is that kind of scenario?
Absolutely.
If Docker is good
Yes.
for running databases?
Absolutely. That's a great use case for Docker. And that's one of the places where Docker shines because it's a lot faster and lighter weight to do that. You know, there's no reason that SQL server needs its own virtual machine separated to just run a quick task and go away. And in fact, another way that you can think about this is any kind of service that only needs to run very processor intensive for a short amount of time is a great use case. So spinning up a cluster of 1,000 Hadoop containers to do some process and then having them go away is something that used to be relegated to the world of virtual machines. Increasingly, I think Docker and containers, you're going to see those more and more in big data.
Thank you.
How does Chef work in this containerized world?
Yeah, so there's lots of room for things. So Chef is a configuration management tool. And there's lots of different ways you can apply something like Chef or Puppet or Ansible in a Dockerized world. So there's a few things you can do. One thing you can do is you can use Chef or Puppet to create the containers themselves. So instead of apt-get install MySQL and tuning it and doing all that, you can add the Chef cookbooks and have the Docker build run Chef for you. So you can reproduce a lot of the same things you're already doing with Chef in a container to generate a container. And then once the run is complete, instead of having to run the Chef cookbook every time, now you can distribute that Docker image everywhere. And the Docker image will spin up in less than a second. But there's also some work being done, and this is still early work, around using things like Chef and Puppet themselves to manage Docker. So using the declarative format of DevOps tooling to include the management of Docker containers themselves. I think that as much as something like Chef or Puppet wants to get into that space, I don't think that they're going to succeed there. They're greatly tuned for managing operating system configuration management, and the world of container management is vastly different. So I think that the born on container declarative models are, in my opinion, are more likely to win, but you can use them either way.
Did you say that Atomic and CoreOS were actually based on Linux SE?
No. So Atomic is based on RHEL, but it's been stripped down. And both Atomic and RHEL have SE built into the Docker support, so that the Docker images have SE support natively. If you're running Docker on a Ubuntu host, you have to set up and manage SE Linux yourself. So you have to configure it yourself. It's kind of built into the box with the Atomic stuff. CoreOS doesn't have SE built in out of the box. Yeah, it might. CoreOS is focused on security aspects, so I wouldn't be surprised if they go there.
A lot of the security aspects that you are describing sound almost too good to be true. Who's doing research on this now? Who can we follow and get smarter about this so we can make recommendations to our clients?
It is really early, and I don't think that there's become. I haven't seen a leader come out yet, and I've had lots of venture capitalists asking the same question. I don't have an answer for them either. As soon as I do have an answer, I'll let you know. So follow me.
I have one quick question. You mentioned about these micro frameworks and also the client-side JavaScript things. So the difference is what is micro frameworks like Go or they are languages, you say.
Yeah.
Go or Simata, or the Angular JS is more like is Go and all those things are to build logics, more like business logic.
Yes.
And the Angular JS, these guys are mostly on UI.
That's exactly right.
We cannot, in some places, can we use both interchangeably, or it's not at all?
Not at this point, because on the client side, the only language that's in the browser is JavaScript.
Okay.
So the JavaScript frameworks are kind of in the browser. Node is JavaScript on the server side, so that's where things can get a little murky.
Yeah,
But,
yeah, that's what I'm asking.
But and there are ways that you can bundle those together. So if you have a Node backend, there are Angular plugins for Node backend servers that make Angular front ends easier. So there is a nice synergy if you're using JavaScript on client and server.
Okay. Yeah, thanks.
Sure.
So this was a great talk. I appreciate your time. Just one question going back to this morning. You talked about infrastructure as a service solutions having a higher failure rate and therefore, build for failure, build for redundancy. Any insights into why that failure rate's higher than we might think it is?
Any insights into why it is higher? Well, I mean, there's speculation. It's hard because a lot of the cloud providers, they don't tell you why, and they're the only ones who know. But speculation is like they're using commodity hardware. So an enterprise might invest in top-tier hardware and put great investment into the infrastructure itself. Amazon and Google aren't. They're using the cheapest stuff they can find. And again, it's speculation based on things they've said, but because of that, things break often.
All right, I think that's all the time that we have here today, so I'd like to give Lucas another round of applause.
Thank you.
Curious to learn a little bit more about what we're doing on infrastructure as a service as well, I'd encourage you to reach out to Manjeet, Nirmal, and myself for questions about things like our project Jellyfish, which is the brokering solution, as well as some of the work that we're doing on GSA, where we're planning to incorporate some of the Docker technology as well. So thanks everyone for joining.